Hello बच्चों, सत श्री अकाल and namaste from my side. How are you all? So guys, this is Indrajit Singh, right? Hope so you like this teaser, and I would be waiting for all of your comments beneath the video regarding this teaser and all of those, right, that went on into the victory batch. So guys, this is Indrajit Singh again, your own physics educator, welcoming you all into the most sensible platform for an aspirants, those who are preparing for JEE NEET kind of examination. Again, we are back with the one short lecture on Newton's laws of motion. NLM, the most important parts of the mechanics. The most important parts of the mechanics, and obviously we are going to deal it with very hard. So, are you all ready with it? Right? Lots of things we are going to discuss, but before moving on to the Newton's law of motion, I want to discuss a small thing with you all, that before, see, the physics labels, I used to deliver this thing into my previous lectures also. The physics thing is designed in a way that the first chapter is a general chapter about the units and measurements. Okay, it is a general chapter regarding the units and measurement. And if I'm talking about the rest of the things, like the second chapter, motion into the 1D, it completely deals with the particle and motion without cause. Yes, students, motion without cause. Now we have also seen, sorry, not now, but we have also seen the motion into the 2D. In all of those cases, right, we have analyzed the motion without cause. But from now, the next part of the mechanics, right, starts. And that is motion with cause, motion with force, that is a cause, motion with energies, and lots of stuff. Motion with the internal configuration of the system. So NLM is all about motion with force. Work energy power is all about motion with the analysis, right? Analysis of a motion, right, through work done through the energies and everything. And the seventh chapter, that is the center of mass and the collisions and the rotation, everything is all about that. The motion with the internal configuration of the system, considering the body, the structural formation of the body, right? Considering the structural formation of the body. Okay, considering the structural formation of the body. So yes, we are going to start with the Newton's law of motion. Now, what things we are going to cover in it? Okay, first of all, I'm going to delete this part. Okay, Newton's laws of motion, right? Basics of it, impulse and linear momentum, and after that we are going to deal with the lots of forces like normal reaction, tension, constraints, pseudo force, friction, and spring forces, right? And spring forces. So shall we begin? Yes, obviously. So the cause of the motion, we are going to start with the cause of the motion, that is known as force. I'm not going to move on to the that much technical definition. First of all, we will have a very generalized approach regarding the understanding of a force. What actual the force is all about. What actual the force is all about. If I want to simply define the force, push or pull. Simply if I want to define the force, then I can define it as push or pull. Right? Push or pull, it means that Sometimes it is a question of the IIT, and many times Alak sir also discusses into the the social media that it is easy to push or easy to pull. Right, this was a question was asked in an IIT. Right, it is easy, whether it is easy to push or pull. Force in another sense can also be called as the cause of the motion. Cause of the motion. Push, pull, cause of the motion. Right. It is a vector quantity. With the vector quantity, right, its unit is Newton. Right? Its unit is Newton. It is behind the name of the scientist, the great, right? Okay, Newton, right, who was the person who actually, right, analyzed, right, that things are gonna get weird for all of those students of the 21st century. He was the first person in the universe who actually, right, internally, spiritually, he defined that all of those lives of students of 21st century are going to be a hell. Yes. Why? Because after a few minutes, apple is going to fall and I am going to discover that gravity. And from that part, after that discovery, obviously it will take some years to do so, but after that discovery, Warana E. Awa. Warana E. And we ayo. Right. So simply cause of the motion, push or a pull, it is the vector quantity and it is right measured in newtons. Right? Newton. Okay. Now, basically Newton's gave the three laws. The first law is completely based on the law of inertia. But before moving on to the first law, okay, we have to understand the concept of inertia, and that is nothing else but the taklif. Right? Nothing else but the taklif. What actual the taklif is? Right? What actual the taklif is? How we can compare taklif to the inertia? What actual the taklif is? How we can compare taklif to inertia? Right? How we are going to compare that part? Okay. So to understand the concept of the inertia, right? See, first of all, if I want to define technically, inertia is nothing else but internal property of matter to resist, right? That resist the state change. Internal property of the matter that resists the state change. A simple definition is it. How we are going to compare this inertia to the taklif? How we are going to compare this inertia to the taklif? That is an important part. How? Right? How we are going to compare this inertia? See, it is a very simple thing. Let us take an example. I was sitting idly and scrolling an Instagram. Let's say about any kind of the social media handle. I was suddenly the students, those who are single, okay, Someone might be saying, sir, we are committed to the IITs. We are in relationship with the IITs. So I'm talking normally about the students, those who are continuously scrolling up the reels of that social media. What happens here? Suddenly, right? Badam, badam, dada kacha, badam. I'm going to get the copyright for it. God knows. Right? The boy and girl. Right? Badam, badam. Something like that. God knows. I'm just dancing. I don't know that part. Right? So one who was scrolling was single. So he felt taklif. He felt taklif, inertia. मैं तो रास्ते से जा रहा था, right? 80 meter per second, 80 kilometer per hour speed, not meter per second, is gonna be quite high. 80 kilometer per hour. Having the headphone in my mind. Suddenly I saw taklif. Why? I can't apply the brakes because it was a highway. If I'm gonna get a stop, the camera is going to take my pictures. Taklif. I was moving at 80 km per hour. Taklif to change the state is inertia. If I was moving at like approximately at 40 to 30 km per hour, then easily I can apply the brakes and can stop for her. But if I suddenly apply the brake at 80 km per hour and right, then what will happen? Badam, badam, dada, phuta, badam. Right? So, taklif. Destiny didn't support me, so that is inertia. Inertia is nothing else but a internal property of an matter to change its state. That is taklif. Internal property of the matter to change its state. It is taklif. Right? Now, how we are going to help that part? How we are going to example? First, early in the morning, body was at rest. The state was of rest. Body was at rest. The state was of rest. Suddenly my mouth, external force acts. External force acts. I was happily living in my old state. That was a state of rest. Suddenly, as because of the external force, I was about to stain, or I was forcefully, right, changing my state. Taklif, inertia. Inertia is nothing else. It is directly proportional to the mass. Right? Okay. A man in bus, right, he faces inertia when driver suddenly applies the brake. Suddenly, if car turns left or right, a man faces the inertia. Right? So inertia, it is nothing else but the taklif. What kind of the taklif? To change the state. If object is at rest, he wants to be at rest. He does not want to change its states. But he is feeling taklif to change its specific state. The taklif is an internal property arising into the matter. Right? And that is nothing else but an inertia. Inertia is of, there is a classification that we are going to discuss. Right? Okay. Three type of the inertia: at rest, motion, direction. I'm going to simply give you all the example, right, to understand that stuff, and immediately we are going to close that part, because lots of things, all of those type of forces and normals, right, and tensions, right, for the massless ropes and with the rope with the masses, everything we are going to discuss. Okay, everything we are going to discuss. Okay, so immediately we are going to wrap up this inertia. At rest, what is going to happen? Inertia at rest. Okay, inertia at rest. So what happens here? See, it's a very simple thing. This is an example, right? A glass, right? A cardboard is placed on it, and on the cardboard we have kept a coin. Suppose suddenly, with the help of an external with the help of an external force, immediately we are pulling back, right? If you are removing that cardboard, that coin will fall down. So coin want to be its right, the original state, that was a state of rest. But as because of this external force applied to the cardboard, he forcefully has to change his states. So at that point of time, while the state change, the internal property of the matter that is acting, it is known as inertia. Inertia at rest, right? Okay. Object want to be in state of rest, right? As of external force, state changes. Here, inertia acts. Inertia in motion, the best example of inertia in motion, right? Mumbai locals. Sometimes. Right? Sometimes. Right. Now suddenly, घाटकोपर 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 बोरीवली दादर 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 घाटकोपर 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 वीटी उतरो. Suddenly when station arrives, is the right, I am in my older state, the state of motion, but suddenly as of some external force, suppose this truck is moving, as of some external force, it suddenly stops, but I want to be in original state. No one likes it, but forcefully till the destination arrives, we have to be in our older state. Okay. Suddenly, as because of the external force, I have to change my state. At that point, right, inertia acts. That is inertia in motion. Another example is, while the moving bus, I can see, oh, my stop, hey, Mr. Conductor, stop, my stop. So when you go, oh, गाड़ी उधर ही जो रुकेगा, like that way he says ना, sometimes गाड़ी stand पे ही रुकेगा, इधर नहीं. So when they, what generally people used to do, from the moving bus immediately they jump off. After jumping off, they run for a while. They want to be in its original state of motion inside the bus, but suddenly, as because of the external force that stop, they immediately jumps off. See, suppose they immediately jumps off and they are not going to run for a while, and immediately their leg bone is going to get broke, fractured. Right. So at that point of time, what happens here, right? They used to run a bit and after that they're going to stop. So in that case, right, I want to be in state of rest. Object want to be in state of motion. Right? As of some external force, the state changes, inertia acts. I am moving aside on the straight road. Suddenly, if I am taking the left turn, my body is having the tendency to move into the straight direction. When suddenly car took left, generally this kind of thing is happening to the day-to-day life. Whenever we're moving forward now, right, if the driver took the left, we tend to move, right, the body suddenly move towards the right. But actually, right, this thing is not the logic behind it. This is not an actual thing happening there. You were moving onto the straight path, suddenly car took left, but the body is having still that psychology that I have to move forward. So as of some external force, body forcefully has to change the direction. Car moved left, actually we are moving straight, but the car moved towards the left. So as of that kind of an right impact of feeling is generated that we have shifted towards right. Inertia in direction. Right. So object want to be in its original direction as of some external force, direction changes. Inertia acts. Right? Inertia acts. Right? So this kind of thing, it is the nothing else but an okay. So this was nothing else but an inertia. Now let's move on to the next part, right? The Newton's first law of motion. Object at rest will be at rest or in motion will be in motion until and unless external force acts on it. Object at rest will be at rest, in motion will be in motion until and unless external force acts on it. Right? This is nothing else but Newton's first law. The Newton's first law is completely based on the Newton's law, right, of inertia. Now let's move on to the next part, that is nothing else but Newton's second law. Right? Newton's second law is completely based on the momentum and the impulse. Right? Okay. The Newton's second law states that the time rate of change of momentum in momentum is directly proportional to external force applied. The time rate of change of momentum is directly proportional to external force applied. In another sense, they are going to say that external force is directly proportional to delta P, the change of momentum with respect to time, right? If change of momentum is measurable, if it depends on the time, then, right, is directly proportional to dP by dt, right, for a very small change. Right, for a very small change. Right, from this, two new things we are going to discuss, right? Completely depends on F is equal to, let's say, dP by dt. On the basis of this two statement, now within like 15 to 20 minutes of this lecture, we are going to discuss the impulse and the linear momentum, the conservation of linear momentum. Momentum you all are aware of, P, that is equivalent to mv. But here, the external force that is equivalent to dP by dt, right? Suppose if dP by dt is not equivalent to 0, impulse will act. Second case, if dP by dt that is equivalent to 0, right, then comes the concept of conservation of linear momentum. If dP by dt that is not equivalent to 0, then impulse acts. If dP by dt is equivalent to 0, it means that no change of momentum. Momentum is the external force on the system is 0. It means momentum is conserved. The second law is based on this single statement, and from this single statement, two concepts arise, right? Two concepts evolves. First, that is a concept of impulse. Impulse is nothing else but a change in momentum, and second, that is a concept of the conservation of the linear momentum. Impulse. The change in momentum of the particle. Right now we are not talking about the system. The change in momentum of the particle, it is nothing else but, right, impulse. What are the examples of the impulse? Right, the first example. Car is at rest. Suddenly, mama, we need to move on, and it starts moving. Impulse is acting. Right. As of external force, car moves from rest. Velocity changes, momentum changes, impulse acts. So in another sense, impulse is nothing else but the change of momentum. For a very small change, or for the very small change, you can also write it as integration of dp. But that we are going to see through the force. On basis of this impulse, we are going to solve some of the questions. The force F acting on the particle of mass m is indicated by the force versus time graph as shown. The change in momentum of the particle over the time interval 0 to 8 seconds will be what? See, this is force versus time graph. If I am talking about the impulse, right, that is equal to change in momentum, then I can also write it as F delta t. So, for force versus time graph, the area is nothing else. Area under graph will give impulse. Area will give impulse. So here if you really want to define that stuff from 0 to 8 seconds, then immediately we are going to define that impulse. Right? How? This is an area A1, this is an area A2, this is an area A3. So impulse, it is nothing else, right? Area A1 plus area A2 plus area A3. What is A1? That is equal to half. What is the base? Into 2. Altitude into 6 plus A2, right? That is equal to what we can say, the 2 from 4. It is 2 into minus 3 plus that area is 4 from 8. 4 into 3. So this is gonna be 6 minus 6 plus 12. It is 12 Newton second. Right? 12 Newton second is a perfect answer for this specific question. Slowly we are going to move on through the sums, right? And we are going to understand the concept. And basically entire chapter depends on the force, the calculation of the tensions, the constraint relations, the pseudo force, right? The frictional force and everything. But yes, things gonna always get changed with the time. Second, a body of mass 3 kg hits a wall at an angle of 60 degree and returns at the same angle. The impact time was 0.2 seconds. The force exerted on the wall will be what? In this question also we need to calculate according to the Newton's second law. We need to calculate the external force applied, right? But the answer is going to calculate it through the impulse. How? See, it's a very simple thing. It is moving with you. It is getting incident at some specific angle, and the same angle it is getting reflected back. So what happens here? I am going to resolve the two components of the force. This is the first one. This is the second one. This is a u cos of 60. this is a u sine of 60. Similarly, coming back, right, I'm going to resolve the another two components, right? Okay, this one, right, and this one. This is going to be u, right, this is going to be u cos of 60 and this is going to be u sine of 60. Actually, you are saying the components of the velocity that are perpendicular to the wall, right, are not changing. Components of velocity perpendicular to wall are not changing. Component to the velocity perpendicular to the wall are not changing. Only the perpendicular component is changing its direction. It means that impulse, or in another sense I can say that the force that is applied, force imparted on wall is as of the perpendicular components only. It is as because of perpendicular components only. Yes or no? It is as because of perpendicular components only. So what will be the impulse? That is equivalent to change in momentum, right? So if we are considering the sign convention, that is m delta v, right? So m into u sine 60 into positive, right, minus u sine of 60, right? So this is equal to m into 2u sine of 60, right? What is the mass? 3 kg, right? Velocity 10 meter per second. So 3 kg into 2 into 10 into root 3 by 2, right? So this is going to get cancelled. Impulse is nothing else, right, but 30 root 3 Newton second. 30 root 3 Newton second. Now what is an external force applied? External force is nothing else but change in momentum by change in time, right? So I must say it is 130 root 3. Okay. The impact is 0.2 seconds, right? So it is 30 root 3 whole divided by 0.2. So that is 150 root 3 Newton. This much amount of the external force is imparted on the wall. And this is the perfect answer for this specific question. This much amount of the external force is imparted on the wall, right? This much amount of the external force is imparted on the wall. Yes or no? Okay. This much amount of the external force is imparted on the wall. Right. So what is the perfect answer? The perfect answer 153 Newton, and this is the perfect. This is how the impulse is calculated for this specific questions. The second part that is completely associated with the Newton's law of motion, the Newton's second law of motion, is the conservation of the linear momentum. How we are going to deal with the conservation of the linear momentum? It is based on the very simple statement. It is based on the very simple statement I wrote to you all, right, when we were discussing the, when we were discussing that part. Right. So what happens? The conservation of, right, when we were discussing the Newton's second law of motion, right, then what happens? Okay, I told you all. If external force on the system is 0, if external force on system is 0, it means that F external is equal to 0 is equal to dp by dt, right? Then the momentum is conserved. Mark my words, I'm only talking about system, not individual particle. We are talking about the system, not the individual particle. System can have two particles, and obviously in maximum number of the cases we are dealing with the 2 or 3 particles, right? System can have the n particles, we are not interested, but we are only interested the momentum is conserved. If I want to write down, if I want to write down the Newton's second law into the vector form, then this is like this way, dp by dt, and that is equal to 0. So in that case, right, second step states the momentum is conserved, right? The momentum is conserved for system, right? Not for individual particle. Right? So in another sense, I also can write it as initial momentum of the system is equal to final momentum. M1 V1 vector, M2 V2 vector, plus dot 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 plus Mn Vn vector. This is a final momentum M1 U1 plus M2 U2 plus dot 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 plus Mn, right, Un. Okay, this is how the conservation of momentum is defined. Okay, this is how the conservation of momentum is defined. Yes or no? Right? On the basis of this, see, everyone knows the statement of the conservation of momentum, but it is important how to apply it. Right? It is important how to apply it. An object, see, we are going to see that this question is asked in NEET 2019. Right? In NEET 2019, this question was asked, and we are going to solve that stuff easily. Right? Immediately, we are not going to waste the time. Right? We are not going to waste the time and solve that part. An object flying in the air with this much amount of the velocity suddenly breaks into the two pieces. Suddenly breaks. Here in the question, right? See, no description about the external force is given. Suddenly breaks. It means that it happens as because of the internal forces. Suddenly breaks, it means that it happens as because of the internal forces. Right? Internal forces. It means that, right, external force is 0. Okay, not on the individual particle, if I am talking about the system. Why? It is a system. Initially, it was individual particle. Now it got broken into some pieces. Momentum is conserved. Delta P into the vector form is 0. Right? Momentum is conserved. It breaks into the two pieces whose masses are in ratio of 1:5. M1 by M2, that is equivalent to 1:5. It means that, right, okay, M1 by M2, okay, in another sense I can also write it up as M1 that is equal to M by 5, right, and M2 that is equal to 4M by 5. Okay, the smaller mass, I'm sorry, M by 6, 5M by 6. Okay, that's a perfect thing. The smaller mass flies off with this velocity. What will be the velocity of the larger piece? Right. What will be the right click to reach up to the solution by reading the question? From what statement, from what word you are going to get the click? Right. That is suddenly breaks into the pieces. Suddenly breaking is means no external forces, no description regarding the external forces given, and whatever happens is because of the internal forces. And if external force on the system is 0, then momentum is conserved. Initial momentum, that is equal to final momentum of the system. Initial momentum, that is equivalent to final momentum of the system. Right? Okay. So it is M1. Sorry for this thing. It's M1 U, or you can say it as M It was moving with the initial velocity. So okay, mu, it broke on into the two pieces, m1 u1 and that is m2 u2. The initial mass was m, right, and it was moving with what speed? 20, 25, minus 12. I'm writing into the coordinate form 20, 25, minus 12 is equal to smaller mass 135, 8, right, m by 6, 135, 8 plus 5m by 6 into velocity vector v. So m is going to get cancelled first of all, right? So this is going to be 20, 25 minus 12, right, is equal to 100 by 6, 35 by 6, 8 by 6, right? Or if you want to write a phi of v by 6, if you want to make 6 common, then that is 120, 150, minus 72 is equal to 100, 35, 8 plus phi of v, right? Solving this, right, okay, solving this, what we are going to do? 120 minus 100, 150 minus 35, minus 72 minus 8 is equal to 5 into v velocity vector. So that is 20, 115, minus 80, that is equal to 5 into velocity vector v. Right? So this is gonna be 4, 5 2s are 10, 2, 23, 23, 5 1s are 5, 5, 16, right, is equal to v vector. So the velocity of the second mass will be 4 of I plus 23 of j minus 16 of k. This will be the perfect answer for this specific question. 4 plus 23 minus 16 of k. A is the perfect answer. Right? This is how the conservation of momentum is applied. Okay? This is how the conservation of momentum is applied. Okay, let's move on to the next question. Explosion breaks a rock into the 3 parts. This is a click. Explosion never occurs as because of the external forces. It always occurs as because of the internal forces. And in this case, yes, the internal forces, right? The external force on the system is 0, right? The external force on the system is 0. It means that yes, momentum is conserved, right? Delta P, that is equivalent to 0, okay, and momentum is conserved. Delta P is equivalent to 0 and yes, the momentum is conserved. Two of them go at the right angles to each other. The first part of mass, right, okay, see, here, what happens? This is M. Among this, two will go right angle with respect to each other, okay. The first part of the 1 kg moves with the speed of 12. This is 1 kg, this moves with the speed of 12 meter per second. The second part of the 2 kg, right, it moves with the 8 meter per second. What the speed of the, right, okay, the speed of the third mass is 4 meter per second. Then its mass is what? Right? Suppose immediately we are going to see that stuff. Okay? How smartly they have played. They have not given the direction of the third particle. Right? How smartly they have played. Okay, so I think let's move on to the solution of it. See, external force on the system, right, is 0. external force on the system that is equivalent to 0, right? So in this case, what happens if external force on the system is kept 0, right? Then the momentum is conserved. Initial momentum is 0, final is P1 plus P2 plus P3, right? Now, mass of 1 kg, see, they both are moving perpendicular with respect to each other. So can I say 1, it is moving at 12 of J, right? 2, it is moving, right, with 8 of I plus P of 3. So P of 3, you are going to get it as a negative of 16 of I minus 12 of J, right? If we are having the magnitude of it, right, if we are talking about the P3 in terms of the magnitude, then we are having 16 square plus 12 square, right? 16 square plus 12 square. How is gonna be, if we're talking about the magnitude, then this is mass into velocity, right, of the third particle. Okay, what is the velocity of the third particle? Okay, it is moving on with the 4, okay, and we need to calculate the mass. Okay, so this is under root of 16 square plus 12 square, right? This is 4, so m3, it is under root of 16 square by 4 square plus 12 square by 4 square, right? So this is gonna be m3, that is equivalent to, right, under root of 16, 4 square is 16, 116 is gonna get cancelled, right? And this is 12 into 12 by 4 into 4, 4 3s are 4 3s are, right? So it is gonna be 9. Okay, so 16 plus 9, m3, that is equal to under root of 25. So m3, that is equal to 5 of kg. Okay, this is the perfect answer for this specific question. This is how the conservation of momentum is applied. Okay, let's move on to the next question onto it. A 1 kg stationary bomb is exploded into the 3 parts. Again, see, m1 is equal to m by 5, m2, that is equal to m by 5, right? m3, that is equal to 3m by 5. It exploded into the 3 parts and the masses ratios are given. Parts having same masses move perpendicular direction with this velocity, right? What is the velocity of the bigger part? Awesome question. Direct momentum is conserved. Initial momentum is 0, final momentum is m1 v1, right, plus m2 v2, right, plus m3 v3. We need to calculate the value of m3, right? They are moving into the perpendicular direction with right, 30. So it's m by 5, 30 of I plus m by 5 into 30 of j plus 3m by 5. M by 5, m by 5, 3m by 5. What is the v3 we need to calculate? M is gonna get cancelled, right? So this is gonna be 6 of I plus 6 of j plus 3 by 5 of v3. So v3, it is gonna be, right, 6 of I plus 6 of j into negative of 5 by 3. Okay, so v3, it is gonna be negative of 10 of I, negative of 10 of j. v3 in terms of magnitude, it is equal to 10 root 2 meter per second. And this is the perfect answer for this specific question. Okay, this is the perfect answer for this specific question. Yes or no? Right? Let's move on to the next question onto it. Newton's third law. Newton's third law you all are aware of. We are not going to waste time on it. Action and reaction are equal in direction. Sorry, action and reaction equal in magnitude and opposite in direction. See, in this chapter, lots of forces we are going to discuss, right? In this chapter, lots of forces we are going to discuss. Like, we are going to discuss first of all the normal reaction, right? Okay, after that we are going to discuss the tension, right? Okay, after that we are going to discuss the pseudo force, right? After pseudo force we are going to discuss the friction, right? After friction we are going to discuss this one pseudo tension. One kx is there and mg is there, right? But mg is very simple. Kx, right, we are going to discuss into the work, energy and power, because it is quite helpful while dealing with the sums of the right springs. Okay, so now we are going to start with the normal, and before moving on to the normal reaction, right, first of all I'm going to discuss the equilibrium of the forces. This defines the case of the balanced forces, right, and unbalanced forces. Case of balance and unbalanced forces with its conditions, right? Case of balance and unbalanced forces, right, with its conditions. Yes or no? Right, because this thing is going to help us a lot into the, right, in understanding the concepts of the mechanics. Okay, this thing is going to help us a lot into the understanding of the concepts of the mechanics. Okay, so let's start with it. The case of unbalanced and the balanced forces, right, equilibrium conditions for the translational motion, the same thing we are going to discuss again into the 7th chapter of the rotation. But here it is important. The entire mechanics is depending on some of the equilibrium conditions, right? What are those? To understand this, let's take an example. This is an object. Here F1 force is acting, here F2 force is acting, this side F3 force is acting, and on this side F4 force is acting. F1, F2, F3, F4. F1, F2, F3 and F4. So here, what does this equilibrium condition states? First, forces are balanced. If I must say the forces are balanced, it means that into the x direction, F1 that is equal to F3, into the y direction, right, F2 that is equivalent to F4. If in terms of magnitude, right, if all of those forces are matching, right, then I must say this is the equilibrium condition. Body is neither going to move into the x direction nor it is going to move into the y direction. Right? Forces are balanced. Case of unbalanced forces. See, if forces are balanced, then net acceleration along the x direction is also 0 and the net acceleration along the y direction is also 0. It means the net acceleration along the x is 0. It means summation of all forces along the x, that is 0, while summation of the all forces along the y is also 0. Summation of the all forces along the x is 0. The summation of the all forces along the y is also 0. Right. Second case, the case of unbalanced forces. Right. The case of unbalanced forces. Right, it means that if summation of the all x forces is not equivalent to 0, it means there exists a net acceleration, right, okay, along the x direction. If F1 is equivalent to F3, right, object is gonna having net acceleration as 0 in the case of the balanced forces. But into the case of the unbalanced forces, right, if F1 is not equivalent to F3, we are going to have the net acceleration is x direction. Similarly, if summation of all y forces is not equivalent to 0, then the net acceleration along the y is also not equivalent to 0. This is the entire case of the right equilibrium of the forces on which entire chapter of NLM depends. Entire chapter of Newton's laws of motion depends. Right? Entire chapter of the Newton's laws of motion depends, yes, on this. First of all, we are going to deal with the normal reaction. Okay. What does the normal reaction states? See, now, this was the fundamentals, the inertia, the classification of the inertia, Newton's first law, conservation. Conservation of linear momentum is again going to come back into work energy and power. Right, conservation of linear momentum and the impulse and a blah 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 were a small chit-put things. Now from now onwards, right, from the equilibrium of the forces, right, okay, the entire chapter is about 5 to 6 forces: mg, normal, tension, friction, pseudo. More about 3 forces: tension, friction, pseudo, and chapter is gonna get over. Tension, friction, pseudo, chapter is gonna get over. So let's start first with the normal reaction, right? Okay, let's start first with the normal reaction. The perpendicular component of the force, perpendicular component, right, of force to contact surfaces, right, to in another sense, to surfaces in contact. This is an exact definition there. Surfaces in contact, okay, it is defined as the normal reaction. Okay, perpendicular component of the, right, forces, right, to the surfaces in contact. Okay, suppose let us take an example. Okay, these are the 2 surfaces in contact, right? Okay, the perpendicular component of the force to this contact surfaces, this is the normal reaction. The name itself states that normal reaction. The name itself states it is the normal reaction. Normal reaction, in another sense, there is an action. Normal reaction, right, it is the reaction force to the action. Normal reaction is the reaction force to the action. Is the reaction force to the specific action. Here, weight is acting into the downward direction. It acts like an action reaction to this perpendicular, right, one force is going on. That is known as the normal reaction. There are lots of ways to calculate the normal reaction. Okay. First of all, we are going to understand the concept, right, how to calculate the normal reaction into the different ways. Okay, a cylinder of the weight W, okay, we are going to calculate the normal through sums. The cylinder of the weight W is resting on the fixed V-shaped groove. See, there is a V-shaped groove. One cylinder of the weight W is resting on it, right? Vertical angles are given to be, right, angles, right, are given to be 60 degree. It means that it is a very simple thing. These angles are given as 60 degree. Right. Then what will be the force? Right. We have to calculate the normal reaction. Calculate the normal reactions between the cylinder and the 2 inclined walls. Before moving on to this thing, I want to teach you all, right, how to draw the FBD. Before moving on to these things, I want to teach you all how to draw the FBD. What actually FBD is, right? First of all, I am this thing you all are aware of. FBD is free body diagram, right? What are the noteworthy points related to the free body diagram, right? It represents all forces on the specific particle or the object or the rigid body. Free body diagram, right, helps us in understanding and solving the problem in mechanics. Just keep one thing into the mind, always this free body diagram should be drawn for the individual system with its configuration or the respective particle. If you are going to draw the free body diagram of the entire system containing more than one or two or more than two particles, you are definitely going to get stuck with it. Third point about the free body diagram, observer position matters. Observer position matters in it, right? Observer position definitely matters in this. Okay. Let's move on to the next part onto it. First of all, let's solve this ordinary sum of the normal reaction, and then we are going to solve that FBD part, right? First, it was important to discuss the FBD with you all. Okay, see now, this is the normal reaction between the blocks N1 and N2 that will be equivalent to what? N1 and N2. Normal reactions, right? First of all, we are going to draw the FBD for it. Okay, this is the 5 kg, right? This is the 20. Okay, I think it's not appropriate to draw it here. Okay, we are going to draw into the else page. Okay. Five kg, 20 kg, 25 kg. On 25 kg, how much amount of the 200 Newton of force is acting? See, we are having only one system acting on this system. It means one thing is fixed. What? Entire system is getting accelerated into the left direction, and all of them, right, are having the common net acceleration. The entire system is moving with the net acceleration. Entire system is moving with the net acceleration. Okay, 5 kg, 20 kg, 25 kg. 5 kg, 20 kg, 25 kg. So in this case, what is going to happen? Right, how we are going to place that normal? This is the normal reaction. Let's say this is N1. Let's say this is N1. This is N2, right? And this is N2. For the action, we are having reaction. For this action, right, we are having reaction. Okay. For 200, we are having the reaction. Now this reaction acts on 20 kg. For this action, okay, we are having reaction. So it is generally not a reactive force, it is also right, okay, but for understanding purpose, right, we can say it as. Now, what is a net acceleration acting on the system? That is equal to net force, right, by mass of the system. The net force that is equivalent to 200 by mass of the 20, 25, 50, 4 meter per second square. In this case, it is important to understand how the equilibrium conditions are applied here. Net acceleration, according to the equilibrium conditions, the net acceleration is not zero. The net acceleration into the x direction is not zero. It means that take the individual block and apply the equilibrium conditions. The summation of the all x forces, that will be equivalent to net acceleration into the x direction. Apply for the individual block. Suppose if you are applying for the 25 kg block. See, keep one thing into the mind. The net acceleration, right, okay, is in direction of the force with the higher magnitude. Right, force with the higher magnitude. Okay, so suppose here the net acceleration is in this direction. Okay, so can I say this at first, if I'm going to pick the 25 block, mass is 25, net acceleration. In the direct net acceleration, in the direction of the net acceleration, the force is of always of the higher magnitude. 200 minus lower magnitude N2. Net acceleration we got it as 4, right? So 100 is equal to 200 minus N2. N2, that will be equivalent to 100 Newton. We got the value of N2. Suppose if we are applying the equilibrium conditions for the 20 kg. 20 into acceleration net, right? 20, see this is how the equilibrium conditions are applied. 20 into the net acceleration A. 20 into the net acceleration A. So that would be equivalent to what? Forces into the higher magnitude N2 minus lower magnitude N1. So 20 into 480, that is equal to 100 minus N1. Sorry. N2, okay. N1 that is equal to 20 Newton. In this case, the value of N1 is 20 Newton and value of N2 is 100 Newton. This is the perfect answer for this specific question. Okay, here N2 is taken and here N1 is taken. Right, we took into the reverse manner. Here we took N1 and here we took N2. This is a small difference. Here N2 is there, N1 is there. By mistake we took here N1 and right in the reverse format we took it out. So that's why the answer is coming. Actually our answer we got it as 20 and 100. But here it is into the reverse manner, right? So please don't mind. The procedure is same, thus the notations are different, right? Let's move on to the next question on the normal. Okay. Okay, now we are going to solve this. Here weight is acting into this direction, then what would be the normal? First of all, I'm going to define the normal for you all. This is a normal reaction from the wall A, right? From the wall B, this is a normal reaction from the wall B. Okay, see now, NA is having the two components. This is NA cos of 60. This is NA, right, sine of 60. Similarly, N of B, sine of 60. This is N of B, cos of 60, right? This is gonna get cancelled. Only vertical components remaining. So that defined as summation of all Y forces is 0. Right, summation of all Y forces is 0. Why summation of all Y forces is 0? Because here the system is in equilibrium, it is not moving. So the net acceleration along the Y is 0. Okay, so it means using this condition we can say that, right, NA cos of 60 plus NA cos of 60, that is equivalent to W. Here NA is equal to NB. Why? Because on the both side it is subtending the same angle. So for that reason we have taken as NA equivalent to NB. So here NA you are going to get it as W by 2 into the both direction, and this is the normal reaction value. The normal reaction is calculated individually just to show you all how the equilibrium conditions are applied and to make you all comfortable with this kind of the conditions. Right, just to make you all the comfortable with this kind of the conditions. Right, let's move on to this one question I'm giving you all into the homework from the normal reaction, and here it ends. Okay, you have to answer this question beneath the video, right? This is a very nice question. Okay, all of these things are given. Okay, now let's move on to the next part. Okay, what actually, right, the tension is. Now let's move on. Have you seen, some students might have seen this game, Squid Game, tug of war, hey, 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 kind of thing, right? Hey, 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 kind of thing. What is a tension, right? What is a tension, right? How we are going to deal with that? How the Squid Game is going to help this stuff, right? How the Squid Game is going to help in this stuff. The most important strategy, right? Okay, the most important strategy was followed by this, what we can say, the hero of the Squid Game, right? You can say the grandpa of the Squid Game, that old guy, right? Okay, now how we can correlate this tension force to the example of tug of war, right? How we can correlate to this tug of war, right? Suppose, let us take an example. There is a rope or a string, right? See, in a tug of war, what happens? One is applying the force, right, in this direction. Can I consider this as F1? Second is applying the force in this direction. Can I consider it as an F2? Now both sides, right, the force is applied. Obviously, right, in tug of war, one is trying to pull the game towards their end. The second is trying to, right, pull the game towards their end. Pull, that is an important word, right? A pull, right, exerted by rope, strings or chain, right? That pull is defined as tension. Pull exerted by rope, chain or any kind of the strings. Suppose in game of a tug of war, one team is trying to pull the right rope towards their side. So against this force, rope is exerting one pull. Suppose if force is applied to this side, against this force, right, a rope is exerting one pull. That pull, see, force is nothing else but a right push or pull, right? So this pulling force, it is a tension, right? This pulling force is a tension, right? Let's have an examples of it. Let us take an example. Suppose a block of mass m is attached to the string or a cable and it is attached to the ceiling. In this case, what will happen, right? What kind of the force it is exerted, right? Okay, suppose let us take an example. Its weight is acting into the downward direction. Can I determine it as mg? Right? Against to that weight, this is a pulling force. Exerted by a rope. Pulling force exerted by a rope. Right, here net acceleration is 0, that's why we are equating the vertical forces, right, because net acceleration is 0. But interestingly, right, we are, right, talking about the pulling force. That is an important part. Either it can be rope, either it can be chain, either it can be string, but tension is a pulling force, right, that is exerted by this kind of systems. Basically, we are having two kind of systems. As I said about tension, right, in summarized form, it is a pulling force Basically for tension we are having two kind of classification. One, ropes with masses m, right? Second, massless ropes. That is the difference. Arey yaar, I'm sorry, this was a black screen. Tension, a pulling force, right? Okay, one, obviously it is exerted by ropes, but in one case ropes are having masses m. Second, massless ropes. There is a small difference between the massless ropes and ropes that are having the masses m, right? Suppose, let us take an example to understand this, right? Okay, this is a rope of mass m that is pulled by force F and acceleration is along this direction, right? This is a rope with masses m. Suppose a mass m is attached to the rope or a string and then is connected to the ceiling. In both of the cases, what is the difference? What actual the difference is? Suppose if I'm talking about the 3 points, point A, point B, point C. Similarly here at the 3 points, point A, point B, point C. If the ropes are having masses m, then tension at the each point of the rope is not equal. Tension at each point of rope is different. Suppose if rope is massless, tension at each point is same. It means in this case, can I say TA that is equal to TB that is equal to TC? Yes, we can say that. Why? Because the rope is massless and each and equal, right, equal pulling force is exerted at the each and every point of the string if the rope is massless. But at this case, I can't say TA is not equivalent to TB is not equivalent to TC, right? Okay, here it differs. Right. So for that reason, into the Pulley problems, it is always mentioned. For that reason, into the Pulley problems, it is always mentioned. Right. What it is mentioned? All pulleys are massless and frictionless. All strings are massless and frictionless. All of these things are massless and frictionless. Why they consider everything is a massless and a frictionless? Because tension at the each point of the rope or string or the chain is equal. Similarly, in this case, tension at the rope or the each point is not equal. Why? It is having mass F. We are going to see both of these cases, right? First, we are going to see this and after that this. But before that, to deal with these cases, right, you are in need or to understand the 3 types of densities. If the ropes are having mass m, then it is important to understand how masses are distributed to solve this sums easily. For that, we are having 3 types of densities. First, linear mass density. That is known as lambda. How mass is distributed over length. In one-dimensional object, how mass is distributed over length. Suppose with respect to the reference point, the length of the string is L. In between 0 to L, how mass is distributed? Is it uniformly distributed? It is non-uniformly distributed. Whether it depends on the equations or not, lot of the things, right, we are going to discuss. So, types of density contains first, right, as linear mass densities. Second one, that is surface mass density. sigma. How mass is distributed over specific area. This is two-dimensional object that contains length and breadth, right? How mass is distributed into the small area element dA. If this mass is dm and this area is dA, then I can also write it as dm by dA. Into the very small element, area element, right? Okay. How it contains and how mass is distributed over specific area. Third, volume mass density. These things, right, are going to quite helpful into the 7th chapter, right? That is rho, that is equal to mass per unit volume, that is dm by dv, right? So this 3 type of densities are quite important to understand this first case of the tension. So these are the 2 most important cases of the tension, and these are the 3 types of densities, right? I'm moving aside because this is a blank screen. You're not going to get into the notes. Don't get worried. You can just have a snap of it, right? It's phi. I'm giving you right on the countdown of the phi, right? You can just, we will move on, right? So it starts 5, 4, 3, 2, 1. Suppose this is a string having mass m, right? Right now I'm not considering this much part of the string, right? I'm not considering, I'm only, right, considering this part. Suppose this is pulled by force F at distance x, right? What will be the tension of this string? Right, at distance x. I'm considering only this much part of the string, right? Because the upper one would be the complicated case that we can see in the sums. Now, as usual, according to our discussion, the rope is having mass m. It means that tension at the each point is not same. Then how tension varies? First, it is a case of a uniform mass distribution. It means lambda, mass per unit length of the system, is constant, right? That is equal to dm by dl. Mass is constant, right? Now let's draw the FBT. Suppose at the, total length of the string is L. Suppose we need to calculate the tension at a distance x, right? So I am dividing the rope into the 2 systems, right? Okay. This one will be M1, this one will be M2, this will be X, this will be L minus X. Now tension is a pulling force. Pulling force, it means direction of the tension will be like this way. Pulling force, it means direction of the tension will be like this way. Force is acting in this direction. What will be the direction of the net acceleration? Direction of the net acceleration will be in this direction according to the conditions of equilibrium of the forces, right? We are having the acceleration into the x direction. It means summation of all forces along the 0, that will be m into a net. If I'm using this first equation, mass 1 into net acceleration, m1 into a, right? Can I write it as force in the direction of the net acceleration, higher magnitude, minus lower magnitude. Similarly, for this second, forces in the direction of the higher magnitude, right? Opposite direction, we are not having any kind of the forces. Can I consider this as equation number 1, right? And can I consider this as equation number 2? Yes. Now, as we said, uniform mass distribution, lambda is constant. It means what? Lambda is constant is equal to mass per unit length is equal to what? M1 by X, M2 by L minus X. I can write it down, right? If lambda is constant, right? And if mass per unit length is constant, mass is uniformly distributed over length. So can I write it as m1 that is equal to mx by L, m2 that is equivalent to what? Right, m2 that is equivalent to m into L minus x by L. Right. So here, and obviously the net acceleration, it is going to be F by m, because it is net force by mass of the system. Mass of net acceleration, we are having net force F by mass of the system is m, right? Okay, now we need to calculate the tension. T is equal to m2a, right? Can I replace the value of m2? M2 value is m by L into L minus x, right? A. Can I replace the value of the net acceleration? Because this is unknown, we need the answer in terms of F. A is unknown, A is an intermediate physical quantity, we need an answer in terms of F. So can I write it as m by L into L minus x, right, into F by m. This mm is gonna, right, this is the tension, right? This is the value of the tension, right? This is how it is calculated, right? Using the equilibrium of the forces, right? Okay, the cases of tensions having mass m, right? Okay, now, so guys, this one and this one, this two, right? Okay, you can do, it's not a big deal, because we need to cover the lots of part. The most important from this, right? Okay, the most important part apart from this is like this one, right? This we can do, okay, this we can do, it's not a big deal. Okay, now let's move on to the Pulley problems. Let's move on to the Pulley problems, right? In a maximum number of the cases of the Pulley problems, right, one word is used: all ropes are massless and frictionless. All pulleys are massless and frictionless. Pulley, it is also known as, sometimes it is also known as Atwood machine. And lots of technical words are there, but we are not interested in that, right? We are only interested right into the, right, what actually the concept says, right? What actually the concept says. So Pulley problems, all ropes are massless and frictionless, all pulleys are massless and friction. So in this, all of these cases, we are directly going to deal with all of those stuff, right, in which all of the cases, right, the pulleys and ropes are massless and frictionless, right? Okay, so these two most important statements, right? Again, I'm writing here, all ropes, right, all pulleys, massless and frictionless. We are going to solve this sum by means of right, we are going to understand this sum by means of this the sums only, right? We are going to understand this concept by means of the sums only, right? Okay, see, two bodies of mass 4 kg and 6 kg are connected to the ends of the massless string. See, it is given massless. In maximum number of the cases, it is massless. The string passes a overlay which is frictionless. Oh, that is frictionless. See the figure. The acceleration of the system in terms of gravity will be what? NEET 2020 they have asked. Very simple sum it is, right? Very simple sum. 4 kg, 6 kg. First of all, I want to ask you all, in which direction the particle is moving? Obviously, this is of the high weight. It means it is moving in this direction, and this is of the less weight. Then the system, this 4 kg is moving into the upward direction. Right? This is just a common sense, right? That 6 kg, right? It is of the higher mass, so it is moving into the downward direction, and 4 kg is of the lower mass, then it is moving into the upward direction. Now, what will happen here? First of all, let's draw the FBD. This is 4 kg. Right, this is 6 kg. First point, their weights are always acting into the downward direction, right? 4G, 6G. Tension is the pulling force. They both are connected by the same string. String is massless. It means tension at the each point on the string will be same. Tension at the each point on the string will be same, right? Because string is massless, as I told you before, right? It is a pulling force. It is a pulling force. So for 4 kg, it will be pulled in upward direction. For 6 kg, it is also pulled into the upward direction. Tension is a pulling force. Now, if 4 kg is moving into the upward direction, it means the net acceleration will be like this way, and net acceleration in this case will be like this way, right? Net acceleration in this case will be like this way. Now, summation of all horizontal forces till now we have seen summation of all horizontal forces are 0, summation of all vertical forces are 0. After that, we saw one example into the normal reaction, that summation of all horizontal forces are not 0 but vertical are balanced. Here there is no horizontal force, only vertical forces are there. So it means net acceleration along the y direction is not equivalent to 0. So the summation of all forces along the y direction will be equivalent to ma net. Right? Right? ma net. Okay. First of all, we are taking 4 kg. So ma net, that is equal to summation of all y forces. What is mass? 4 kg. What is net acceleration? A. In the direction of the net acceleration, force is of higher magnitude. Opposite to that, lower. Higher, lower. Can I consider this as equation number, right, 1? For 4 kg block, right? Suppose if I am moving on to the 6 kg block. Suppose if I am moving on to the 6 kg block, right? So can I write it as mass into net acceleration, that is equal to summation of all Fy forces. Mass is 6 kg. Net acceleration is what? Right? A. Force in the direction of the net acceleration is of the higher magnitude. Here 6g is the higher magnitude minus lower. Equation number 2. Can I equate them, right, to calculate the tension and the net acceleration, right? So it's 4a is equal to t minus 4g. 6a, that is equal to 6g minus t. Right? So it's 10a, that is equal to 6g minus 4g, right? That is 2g. A is equal to g by 5. The net acceleration of the system is g by 5. Right? The net acceleration of the system is g by 5. If you don't want to equate it, right, you can we are having the second procedure also. If you don't want to equate it, right, okay, so you can just replace it also. Suppose t is equal to 4a plus 4g. 6a is equal to 6g minus. Can I replace value of t as 4a plus 4 of g? So it's 10a is equal to 2g. Again, a will be g by 5. This is the second. You can replace second equation in one or one equation in second. Right? Okay. Now what will be the value of the tension if a is equal to g by 5? It's very simple. Right? We are going to get the tension as, right, 4a plus 4g, right? So it's 4 of a plus g, right? So tension will be 4 into is g by 5, right? So 6g by 5, right? So 60 by 5, 12, 48 Newton will be the tension, right? Acceleration is g by 5, tension will be the 48 Newton. Okay. Second sum. Let's move on to this kind of the concept, right, and calculate the tension. The equal weights, right? See, first of all, we are going to move on with the fixed pulleys. See how tension rules. Mass, massless, right? Masses, we did the calculation. We moved on to the types of densities. Massless, right? Fixed case, movable pulleys, like this way. See, I'm going to show you the tension, right? Masses, massless. Massless fixed pulleys. For movable pulleys, we are having constraints. Like this way the flow chart follows. Right? Like this way the flow chart follows. Right? Now let's see this question. The three equal weights of 2 kg are hanging on the string passing over the fixed pulley as shown into the figure. What is the tension into this? Okay, between B and C, right? What will be the tension? String changes, tension changes. See, all the strings are massless. A and B, they are connected by the same string. So the tension at the each point will be same. At this side, tension at the each point will be same. But B and C, they are connected by the different string. I can understand it is a massless, right? But still tension will differ because tension is the pulling force. So between B and C, we are having the tension as T1, right? So let's discuss each of the masses are 2 kg. See here, it's B, it's A. 2 kg, it means their weight is acting in downward direction. 2g. The weight is acting into the downward direction. Obviously, they are connected by the same strings, right? So they are having the same pulley force, T. Right? Okay. Now we are having C. C is also, right, 2 kg. So its weight is acting into the downward direction, that is 2g. Right? Now see, between B and C there is a string, right? So in between them, right, there is also one pulling force, right? That is pulling C towards upward and B towards downwards, T1. Now most important, what is the direction of the net acceleration? Obviously, on the right side of the system, we are having the higher masses, right? So A will move into the upward direction with net acceleration A. B will be moving with the downward direction and this will move with the downward direction with acceleration A. Right? Directly write down for the equation. For A, can I write what is the mass 2 kg into net acceleration A? In the direction of the net acceleration, force is of higher magnitude minus lower 2g. For B, right? Can I write mass 2, acceleration A, right? In the direction of the net acceleration, we are having, right, forces of higher magnitude, T1 plus 2g, minus lower magnitude T. Similarly, this, mass 2 kg. In the direction of the force, we are having 2g, right, minus T1, right? So can I write it here as T1, that is equal to 2g minus 2a. Can I consider this? See, can I consider this as equation number 1? Right? Can I consider this as equation number 2? And this is equation number 3. Replacing 3 and 2. Can I say 2a, that is equivalent to what? Right? 2a, that is equal to T1 plus 2g, right, minus T. Can I replace 2g minus 2a? So it is 2g minus 2a plus 2g minus t. So 2a, that is equal to 4g minus 2a plus, minus t, right? So t will be equivalent to 4g minus 4a. Can I replace this in equation number 1? Yes. 2a, that is equal to t minus 2g. So 2a, that is equal to 4g minus 4a minus 2g. So it's 2g 6a. A is equal to g by 3. Net acceleration, we got it as g by 3, right? Net acceleration, we got it as g by 3, right? Now we are going to replace and get the values of, right? What will be the tension? See, we need to calculate a tension between, it's 2g minus 2a, right? It's 2g minus 2a. So can I write T1 that we need to calculate 2g minus a. So it is 2, right? G minus, right? G by 3. So it's 2 into 2g by 3. It's 4g by 3. Right? This will be the tension into the string B and C. Right? 4g by 3. If you want to evaluate it, right, it's 40 by 3. Right? Yes, approximately it is 13.3 Newton. Approximately 13 3s are 39, na? Right? 40 by 3, so it's approximately equivalent to 4g by 3. If I'm taking exactly g value, right, then we are getting 13.3 Newton as a perfect answer. Right? So this is how this sum is evaluated. Now let's move on to the next sum. Right? These are all the basic Pulley problems you all are aware of. After that, we are going to see the constraint methods. Right? After that, we are going to see the 3 methods into the constraint, and slowly we are going to solve these sums. Right? Okay, I think okay, let's move on. Right? As you can see, right, approximately, right, 2.5 hours of the lecture has been completed. Okay, now let's move on to two bodies of masses 5 kg and 4 kg. They are arranged, right, and the tables are perfectly smooth. Ropes are massless and frictionless. The bodies into the case, the accelerations into A and B will be what? Right? See, it's a very simple thing. Same procedure we need to follow. Here, obviously the 4 kg is like this way. The system will move like this way because all the surfaces are frictionless. And here the system will move like this way. This will be the net acceleration, right? And this will be the right net acceleration into the upward direction. And for this kg, net acceleration will be in downward direction. Tension is the pulling force. Tension is the pulling force. Tension is the pulling force, right? Tension is the pulling force. Can I consider this as case A and this as case B? Let's write down the equation for case A, right? For A, can I write down the two equations? Simple, right? 4g, that is acting into the downward direction, mass into net acceleration, 4a, right? Okay, mass into net acceleration. In the direction of net acceleration, we are having the force of the higher magnitude. 4g, net acceleration is downward direction, the 4g is in downward direction, so it is of the higher magnitude. For this, phi a, that is equal to t. 9a is equal to 4 of g. Acceleration in the a, that is equal to 4g by 9. Right, we are having, I think we got the option, but it's okay. We are going to identify for b also. So in this case, acceleration is 4g by 9. Now we are going to write down this for this equation, right? For phi g, and this is for 4g. This side net acceleration is in downward direction. So phi of a, that is equal to phi g minus t. For this, the net acceleration is in upward direction. So it is 4a is equal to t minus 4 of g. This t is going to cancel. This is g. 9a, a in the case of b, that is equal to g by 9. Acceleration into the A case is 4g by 9. B is a perfect answer. The simple Pulley case problems. Right? Kerala PMT 2002. One sum came on Lami's theorem. Exciting theorem is there. Right? It's quite. A body of weight 2 kg is suspended as shown into the figure. The tension T1 into the horizontal string will be what? Tension T1 into the horizontal string will be what? Right? Okay. Tension into the horizontal string will be what? Let's first of all, let's understand this Lami's theorem. What does the Lami's theorem states? Lami's theorem states that first, system should be in equilibrium. Second, Only three forces should be there. F1, F2, F3. Alpha, beta, gamma. The resultant of the three forces is always zero because system is in equilibrium, or in another sense you can write it down F1, right, by sine or alpha. If you are considering this force F1, then angle should be, right, angle should be in between the rest of the two forces. If we are considering F1, right, then angle should be between F2 and F3. If I am considering F2, then angle should be right between F1 and F3, that is sine of gamma. If I am considering F3, then angle should be between F1 and F2, that is sine of beta. This is what the equation of the Lami's theorem is. How to identify whether right to apply the Lami's theorem or not? How to identify whether to apply the Lami's theorem or not? There is an existence of the three forces at a junction, right? And the system is in equilibrium, the net acceleration is zero. This is what Lami's theorem is all about, right? So in some of the cases we can directly use, right? In some of the Pulley problem also we can use this theorem, right? Okay. So now let's move on to this, how to solve this stuff. First of all, let's draw the dB. See, suppose here if the tension is T, right? Then obviously this is 2G. So this value of system is in equilibrium, this T will be equivalent to 2G. I'm talking about one junction. T1 is in this direction. 2G is in this direction. T2 is in this direction. Suppose this is 30 degree. This is 60 degree. This is 90 degree. This is 90 degree. This is 90 degree. System is in equilibrium also, and at junction three forces are there, 2G, T1 and T2. System is in equilibrium also, and at junction, right, three forces are there. Right, directly we are going to apply the Lami's theorem. Suppose if I am writing T2, right, the forces between them, sine of 90. If I am talking about T2, then forces between T1 and 2G, sine of 90. Right, if I am talking about T1, forces, the angle between the rest of two, that is sine of 90 plus 30, right? And if I'm writing, right, 2G, okay, then angle between them sine of 90 plus 60, right? So this is what the Lami's theorem is all about, right? Again, I'm going to write the equation T2 by sine of 90, that is T1 by sine of 90 plus 30. So T1 by sine of 90 plus 30, that is cos of 30, right? And 2G by sine of 90 plus 60, that is T2 whole, 2G, right, whole divided by, right, cos of 60. Now, consider this is equation 1, this is 2, right, this is 3. Compare 2 and 3. Because we need to calculate the tension in horizontal stream. T1 by cos 30. Cos 30 is root 3 by 2. And that is equal to 2G by, right, half. This half is going to cancel. T1, that is equal to 2 root 3 of G. Right? 2 root 3. Okay. It's kg weight. Right? It is asked in kg weight. So it means C will be the perfect answer. This is, we are getting in Newton. Right? To convert into the kg weight, you can just replace G. You can just remove G. Okay, so it will be converted into the kg weight because we have asked into the kg weight, right? So 2 root 3 C will be the perfect answer. Kerala PMT 2002 question, right? Okay, now let's move on to the next question of this. This is asked into the AI 2002. So this is my homework question, right? You can easily solve, right? Okay, you can answer this question within the video. Now, what if the constraint relations are there? What if, right? I'm talking about the constraint relations. Constraint relations mean what? Right? What cases are included in this? So if I'm talking about the constraint relation, first of all, constraint relation means what? One is restricted to move as because of another. One is restricted to move as because of another. Constraint, the word itself states that. Constraint. Second, maximum number of the cases this happens in the case of movable pulleys. See, you can see in this visualization, someone is trying to pull. So as because of this object is constrained to move into the upward direction. It's forceful to move into the upward direction. Right? So this is the case of the constraint relation. Right? This is the case of the constraint relation. Basically, there are some methods into the constraint relation and there are some sign conventions. We are directly going to deal with all of those stuff. Right? Okay, see, 3 methods are there. First of all, the most important method is length of string. This is the most important method. But this is so lengthy, right? Then it is going to consume your maximum amount of the time of the paper. It is that much lengthy, right? So I never used to discuss this, right? We are directly using this 3 important, right? Okay, the first one is a method of work done by tension. Second, it is a method of general constraint, right? And third, up to the advanced level, we are having the wedge constraint. The 3 important techniques are there. The 3 important techniques are there. Work done by the tension, general constraint, wedge constraint. Apart from, see, the length of the string method. Using the length of the string method, we can even calculate, we can solve all of those sums, right, of the general constraint and work done by tension, right? We can solve all of those sums, right, of this, okay, and this by using the length of the string method. But this is quite complicated, right? This method is quite complicated and it is really at the first sight, it is really, right, no one is unable to understand that. Wedge constraint, it is a simple. So for that reason, right, we are discussing directly 3 shortcuts one by one, right? Work done by tension. First of all, let's have this example, right? Let's have this. Suppose this is a pulley. This kind of the system it is given, right? If I am talking about our previous cases, right, a simple classification, simple differentiation I'm going to give you all. See, in all of these cases we saw, right, okay, in all of these cases we saw, see, in for both of the objects, right, accelerations, the net accelerations values were same. You can see here we have taken A, here we have taken A, right, here we have taken this in both of these cases, right, here we have taken upward A, downward A, like this way A, right? Why? Because both blocks were connected to the same string that were crossing over a single pulley that was fixed. It wasn't a case of movable pulley, right? See, in this case, pulley is movable, right? This pulley is movable. So it means that, see, this is fixed. This is going to be into the accelerate towards the right direction. This is going to accelerate it in the downward direction, but these accelerations will be different. This will be A1, or you can consider, right, this as A2 and this is A1. Right, acceleration of the both will be different because they are not connected even to the same string. Even they are connected to the same string also. Then also, right, as there are some cases, we will discuss this, don't get worried, right? As they are connected to the movable pulley, right, the things get differ. How work done by tension, we are going to use that. For 2M, suppose if I am drawing the FBD, right, see. Tension, it is in upward direction, right? Okay, now suppose this 2MA is taking the displacement dA1, or you can say suppose it is having the displacement, right, dx1 into the downward direction, slightly displaced by dx1. Similarly, if I'm talking about mass M, the tension is acting like this direction, and suppose it is, right, displaced dx2 in this direction. 2M is displacing in downward direction and this is displacing in right direction. So are tensions in both in equal? No. Suppose here if tension is acting as T, so it means here tension is T, this will be T. To balance the situation, right, here tension will be 2T. So here the actual tension is 2. So first step is to draw the FBDs, right? First step is to draw the FBDs. Here draw. Now, work done by all tension is 0, right? Work done by all tension is 0. Let's see it here. Work done by all tension is 0. For this block, what will be the tension? 2T. What will be the acceleration? A1. So can I say, let's move on to the, for it's 2T. See here. The force 2T is acting in upward direction, displacement is in downward direction. Force and displacement, they are both in opposite direction. Work done will be negative. So this will be negative of displacement dx1. Here T is in right direction, the displacement is in right direction. So work done is positive. T into dx2 is 0. Can I equate 2T, that is dx1 is equal to T dx2. T is going to cancel. 2 dx1 that is equal to dx2. Can I differentiate with respect to time? I will get 2 of V1 that is equal to V2. Again differentiating this stuff, right? I am getting the acceleration 2 of A1. That is the constraint relation. How one is restricted to move as because of another. By what equation I can represent that equation, right, is known as constraint relation, like this. Work done by tension is always 0. Right? Work done by, right, tension is always 0 in this system. I'm talking about the entire system, not about the individual particle, right? I'm talking about the entire system. Right? Don't get worried. This was an initial stage, right? Okay. So we are having the two important things, right? We are having the two important things. First, either we can directly use, say this is a work done by tension sigma T dot dA, the product of tension and displacement. If really you want to pile up this thing, simple. Tension acceleration of 1, tension acceleration of 2. That's it. For the two blocks, what will be the tension of the two blocks with the respective acceleration? Just compare directly to get the constraint relation. See how easily we are going to use this method, right? Okay, to solve this stuff. Very simple. Suppose tension is T, right? The same string tension will be T, here tension will be T, here tension will be 2T. Obviously, okay, see, the blocks A and B having masses respectively are connected by the arrangement shown into the figure. Calculate the downward acceleration of the block B. Assume that pull is, see, they have asked downward acceleration of the block B. So this is, let us take an example. This is acceleration of AB. This is acceleration of A1. Simply we are going to write, okay, simply we are going to discuss. See, summation of T dot dA, right, that is 0. Directly we are going to compare T1 A1, that is equal to T2 A2. Tension on this will be 2T, right? A of 1, that is T, or A of A, and that is T A of B. So we are having the constraint relation of twice the acceleration of A, that is equal to twice the acceleration of B. Now why this is happening? Because mass of B is greater than mass of A. Generally A has to move downward, but there is a possibility that mass of B is greater than A. That's why it is pulling entire system in this direction. Under what condition will under what condition the A will move into the downward direction? If mass of A will be slightly greater than B, slightly, or right, slightly greater or less than B, right, under this condition it will move into the downward direction, right? See, now same thing we are going to use for this kind of the complicated equations. Very simple, direct constraint relation. This is a A2 and this is A1. See, in this A1 is moving into the downward direction. Suppose this is tension T, this will be the T, right? This will be T, this will be T, this will be T, this will be T, this will be T. Because all strings are same, so, and they are massless. So the tension at each point of the string will be equal. So if this T, this will be 2T. This T, this will be 2T. This T, this will be 2T. So we are having the system like, right? This is an object having, right, acceleration A1, tension is 60. This is A2, tension is T. Directly work done by tension. See, work done by tension states, right, the product of tension and displacement is 0, the net. We can differentiate it twice to reach from displacement to acceleration. But to save our time, we can directly use that stuff. What? T1 A1, that is equal to T2 A2, right? 6, right, of T of A1, that is equal to T of A2. T is going to cancel, right? We are going to have the constraint relation as 6 of A1, that is equal to A2. This is how constraint relations are obtained, right? This is how constraint relations are obtained, like this way. This we have seen, right? Now in this we need to calculate the acceleration. Till now we have seen, right? Till now we have seen how to obtain the constraint relation. See, first of all, let's obtain it. Suppose this is T acting in this direction. This is acceleration A2. Suppose this is T at 2T. This is T, then this is T, this is T. T, to balance this we are having 2T. And this will be A1 into the downward direction. So according to the constraint relation, sigma T dot dA is equal to 0. T1 A1, that is equal to T2 A2. Right? So can we have, right, T of A2, that is equal to 2T of A1. T is going to cancel. We are having A2, that is equal to twice of A1. Right? What we need to calculate? We need to calculate the A2. We will. Let's draw the FBD. This is A2. For this, I am going to write the summation of all x forces is equivalent to m into net acceleration T. Equation number 1. Right? For this block, 2m. A1, that is in downward direction, 2T, that is in upward direction, 2 mg that is in downward direction, right? So for this I can write 2ma1 that is 2 mg minus 2t. So we are having the two equation. First one, that is t is equal to m of a2. Second one, ma1 is equal to mg minus t. ma1 that is equal to mg minus t, right? Let's evaluate it, right? It's t ma2, right? T is gonna cancel, right? M is gonna cancel. So G will be A1 plus A2. What we need to calculate? We need to calculate A2. Can I replace A2 as 2A1? Right? See, suppose A2 as 2A1. This is what constraint relation is, na? So we are going to replace this relation here. So A1 will be A2 by 2. So G will be A2 by 2 plus A2. So it's 3A2 by 2 is G. So A2 will be 2G by 3. B. Into the fixed pulleys, acceleration of both were same. Into the case of movable pulleys, into the constraint relation, acceleration of both are different. So in case of the simple pulleys, what we are doing, right? Okay, see, I'm going to show you all, right? In case of the simple pulleys, see, in the case of simple pulleys, what we were doing, right? We were doing, see, this is acceleration of first, second, both are equal, right? We were just comparing the equation, right? And getting up the answer. Just one extra step we need to do into the case of the constraint relations, right? What kind of an extra step, right? Let's see. See, accelerations are different, so the extra step is to obtain the constraint relation. Same, we have to apply the equilibrium of forces for both, summation of the x and y forces kind of thing, right? We obtain this two equation and one extra step to add the constraint to replace the constraint relation in this to get the acceleration, because acceleration of the both will be different. Find the relation between the acceleration of the blocks into the figure. The pulley and the strings are massless and frictionless. Okay, method of general constraints, what it states. See, before that we moved on, right, to the some of the important, the first method that is work done by the tension, right? General constraints, right? It is having two kind of shortcuts, right? First of all, that is a pulley based shortcuts, right? The first one, that is a pulley based shortcut, right? Okay, now let's see what it states. See, I'm directly write it down, pulley shortcuts. See, this kind of the things, right, can be easily solved by means of the length of the string method also, right? This kind of the things can easily be resolved by method of the strings also, but right, that, as I said, that procedure is quite long. So this is very simple. Suppose this is a pulley. I'm talking about the complete movable pulley, right? This arm, right, it is having the velocity v1. This arm is having velocity v2, and this arm, let us take an example. Okay, let's erase it. Let's keep it this v, right? Okay, this is v1 and this is v2. Similarly, if we are talking about the acceleration, then this arm is having acceleration a1, this arm is having acceleration a1 and a2, right? I'm going to show you the shortcut first, and we are going to discuss the sum, right? Okay, so yeah, we are having the two equations. What kind of this, what are those? V is equal to v1 plus v2 whole divided by 2. This is the first constraint relation. Second, A is equal to a1 plus a2 whole divided by 2. Right, this is the second constraint relation, and it can be obtained, right, by means of this movable pulley method. Sorry, the movable pulley length of the string method. But generally we are not interested into the theoretical approach, right? So that's why we are right directly right using this shortcut. We are directly using this shortcut, right? Now in this method, right, the most important stuff is of the sign convention, right? Okay, the most important stuff is sign convention, right? How to apply it, how to get through the sums, right? I'm going to, right, show you all. For sign conventions, we are having the very simple stuff. If the vector is in upward direction, we are having positive. If the vector is in downward direction, we are having it as a
negative. If vector is in the right direction, we are saying it as a positive I. If vector is in left direction, we are saying it as a negative I. Right?
Sign conventions, equations, and we are going to solve the sums. Now let's move it.
Let's have an example of it. Suppose this is a thing is given.
Right? Suppose this thing is given.
It is given that velocity of this arm is 5 meter per second. Velocity of this arm is 1 meter per second. What will be the velocity of this arm?
This is a kind of the constraint relation. A simple example, right? Not as much as difficult what we are thinking right now. Okay.
So first of all, we are having the two pulleys, pulley number 1 and pulley number 2, right? So we need to apply the shortcut first of all for pulley number 2, right? For pulley 2, right? See, this arm is moving downward with 5 meter per second, right? This arm is moving upward with 1 meter per second, and in another sense, this arm will move downward.
Whether it will move downward or upward, right? According to my experience, I'm saying, but we'll apply the formula and get it.
According to our shortcut, V is equal to V1 plus V2 whole divided by 2. V1 is in downward direction negative, V1 is in upward direction positive whole by 2. V is in downward direction, that is equivalent to 2 meter per second. So here the velocity of this arm is 2 meter per second. Negative indicates according to the sign convention it is moving into the downward direction. If now see, this strings and this strings are same. If this is moving into the downward direction, then tension at the each point will be same, right? With respect to that, the string is completely massless. Obviously all the motion parameters on this will be same. So this will right, okay, this is moving downward, so this will move upward with the 2 meter per second speed.
A very simple explanation and the use of the formula.
The first sum.
Sometimes students are so see, after practicing, right, they used to get a habit for solving this kind of stuff, right? They used to get habit to solve this kind of stuff very easily, right?
Suppose I'm taking another example for this.
Right? Okay, this is also movable, right? This is also movable. Let us take an example. This is also movable.
What will be the velocity at this end? Suppose this is 6 meter per second, right? This is 1 meter per second, right?
Okay, let us take an example. I'm releasing it, right? Okay, this is okay, 2 meter per second upwards, right? This is 1 meter per second, right? And this is 8 meter per second upwards, right? This is the situation given.
Now 3 pulleys are there, 1, 2 and 3. For 3 pulley, can I write directly the equation V is equal to V1 plus V2 whole divided by 2. 6 into the downward direction, 2 into upward, minus 6 plus 2 whole divided by 2. So this will, we are having into the downward direction as 2 meter per second. Similarly for this, right, 8 minus 1 whole divided by 2, right? So this is 7 by 2, right, into the upward direction. Now we are having the pulley as like, this is a movable pulley, this is V, right? This is 7 by 2 into the upward direction, right? And this one, that is 2 meter per second into the downward direction. So V will be equivalent to negative of 2 plus 7 by 2 whole divided by 2. Right, negative of 2 whole divided, right? So this will be V is equal to, right, 3 by 4 meter per second. So what will be the velocity at the top? 3 by 4 meter per second. Positive, it means it is moving upward,
right? So this kind of the first shortcut of the general constraint is. Second shortcut,
suppose this kind of sum has been asked. right? This is theta 1, this is theta 2, this is velocity v1, and this is velocity v2. See, one is restricted to move as because of another. This is the second method of the general constraint in which we are going to see. See, they are connected by the same strings. How we are going to solve this type of sums? Note. How we are going to solve this type of sums? The component of velocity that lies along string is same. Why? Why? This is a note to solve this sum. This is a kind of a shortcut to solve this sum. It's not a big deal, but why? Why the velocity components that lies along the right string are same? Because string is massless. Tension on each point is same. This we are completely aware of. String is taut. It is not loose. It is completely taut. And when the string is completely taut, both are restricted to move in the respective directions. Then the velocity components that lies along the string do not contribute into the motion of this two. And for string to be completely taut, that components are equal. So it means that if I'm drawing FBD for this, right? If I am drawing FBD for this, see, suppose this is right block 2, right? If I'm extending this is theta 2, right? Okay, so it is moving like this way. This is V2. Okay, so this is also theta 2. So this component will be V2 cos of theta 2. Similarly, this is V1, right? And this will be V1 cos of theta 1. So the components of the velocity that lies along the string, right? You can see this lies along the string, this lies along the string. They are equal, right? Because string is taut and it is massless, right? So what will be the constraint relation? V1 by V2, that is equal to cos theta 2 by cos of theta 1, right? So this is the second method of the general constraint. The first method I show you all for the Pulley that shortcuts, right? The second method is this. Now we are going to solve this sum, right, according to this method. See, in a figure, a ball of mass m1 and a block of mass m2 are joined together with an inextensible string. Ball can slide over this if v1 and v2 are the respective velocities of the given, then determine the constraint relation between two. Determine the constraint relation between two. Strings are taut. Simple, you can just memorize it as the strings are taut. So the components that lies on the string are equal. Strings are taut. So the components that lies along the strings are equal. Simple. How to solve this sum, right? Okay, note components, velocity components, or you can say the parameters, or you can say simple, either it can be anything, right? We are just simply defining it as a components that lies on string are same. So it means that suppose if v1 is in this direction, I'm extending this line, so this one will be the theta, right? So d1 will be v1 cos of theta. This is v2, right? So both of the components that lies on the string, simply I can write it as v1 cos of theta, that is equal to v2, right? This will be my perfect answer, right? So this is the second method of constraint, right? So first we moved on, right, to the very simple, right? The work done by tension is 0, right? Work done by tension is 0, and after that we moved on to the method, two most important shortcuts of the general constraint, right? And now we are moving forward to the right wedge constraint. Like general constraint is having one concept, like sigma t dot dA is having one right main concept, the wedge constraining is also having the Brahmastra. As I said before, that's two strings. See, into the previous question, suppose, see, let us take a very simple example. In this,
One is restricted to move as because of another. One is restricted to move as because of another. So in this case, what is happening? The components that lies on the string, as the string is completely taut, both blocks are connected to it, so the components are equal. This thing we need to keep up into the mind. The same thing is happening into the next part, into the concepts of the wedge constraint. See, let us take a very simple example to understand this. Suppose this wedge is given the force towards the right side. If this is given the force towards the right side, then and then this block has to move up. Suppose if this force is given to the right side, then block has to move up. So as because of this block, the upper one is constrained to move. As because of the horizontal, the vertical is constrained to move. Right? It is constrained to move. Right? Okay. Now let's. One is restricted to move as because of another. The horizontal is applied the force, and as because of that, vertical is restricted to move. But you can just have one thing. Vertical is like adjusted this way, right? And horizontal is like adjusted this way, right? This is how you can see, right? The one thing is common in both. They are not leaving contact with each other. Right? They are not leaving that contact with each other. Right? So as because of this is an important concept. Right? Suppose, let's take an example. Right? This is a vertical and he has to move into the upward direction with acceleration A. Right? This is an horizontal, right? And it has to move right side with the acceleration A2. Right? So whatever the components that lies, right, perpendicular to the contact surface, right, the components of the acceleration that lies, right, the components of the acceleration that lies perpendicular. Here I am writing the statement relative of, right, I am writing down the statement again. I think it's visible or not. Okay, relative of components that lie perpendicular to contact surface is 0. Why? Why? Because both of the blocks, see, both of the blocks are restricted to move, but still they are connected by any intermediate thing. In previous case, right, they were restricted to move with respect to each other, but they were connected by strings. In this case, they are restricted to move with respect to each other, but they are connected by the contact surfaces. So perpendicular component will not contribute into the motion with respect to contact surface. Right? So it means that suppose this is theta, right? So this is A2, this is also theta, this component will be A2 sine of theta, right? Similarly, the upward is A1, right? So with respect to this, okay, this will be A1 cos of theta and this will be A1 sine of theta, right? So similarly, right, I will write this into the right appropriate manner. See, perpendicular, right, this is A2, if this is theta, right, okay, then this one is theta, so it means that this will be A2 sine of theta, right, and this will be A2 cos of theta, right? Similarly, the upward is A1, right, so this will be, right, A1 cos of theta and this will be A1
sine of theta.
Right? Okay. Okay, hope so. If I am not done anything wrong, the upward is A1, right? Let's see. Okay, see, this upward is A1 and this is theta, right? And this is theta. Yes, this is theta, right? Okay, it's exactly perfect, right? So it means that it's very simple, right? It's very simple, right? Okay. The perpendicular component of this, it is A2 sine of theta. Perpendicular component of A1, that is A1 cos theta. Relative of this is 0. A1 cos of theta, that is equal to A2 sine of theta, right? So A1, that will be equivalent to A2 tan of theta. This is the wedge constraint problem. Wedge constraint. Okay. Don't get worried. We are going to see the two examples related to it. We are going to see the two examples related to it, right? Find the relation between it's not plus, it's A and B, right? The same thing we need to keep into the mind, as both of the objects are not leaving their contact. So relative of perpendicular components along the perpendicular components across the contact is 0. Let's draw the FBD for this. This is a contact. One that is in downward direction, that is A. Second that is into the right direction, it is B. Right? Okay. Now suppose this is theta. Right? If this is theta, I am plotting up the components. Right? This will be B of cos of theta. This will be B of sin theta. Right? Okay. This will be, right, B sin theta, and this will be, right, okay, it's simple. This is a contact. This will be our contact surface, right? This will be our contact surface, right? Now suppose this is A, then this will be A of cos of theta, and this will be A of sin of theta. Relative of perpendicular components. Relative of A cos of theta minus B sin of theta is 0, right? Relative of perpendicular components. Relative of perpendicular components, right? Relative of perpendicular components, right? So it is A cos theta, that is equal to B sin of theta, right? So A is equal to B tan of theta, right? And that is the perfect answer for this question, right? That is the perfect answer for this specific question, right? A is equal to B of tan theta, right? A cos theta, B sin theta. Okay, you can just see, right, where drawn this component, right? Okay, now let's move on to the another example. See, same thing. This A is moving onto the downside, B is moving towards the right side, right? So this is a homework, right? You can solve it and answer beneath the video, right? So this is the complete the tension part is. This is the complete tension part is, right? Okay. Let's move on to the concept of the pseudo force, right? The concept of pseudo force. Pseudo force, see, till now we have seen, right, all of those concepts of the tensions and everything, right? Generally, pseudo force is explained at the end of this chapter. Pseudo force is explained at the end of this chapter. But what happens, right? I'm going to, generally it is explained by after friction, but I'm going to explain before the friction, because in lots in the friction, lots of these sums are going to come. Okay, that will help us in understanding, right, in which in summarized form, in which the pseudo force is involved, right? The pseudo force is, right, indirectly involved. So that's why, right, we are going to explain it before. Pseudo force is nothing else but the fictitious force, right? Pseudo force is nothing else but the fictitious force. This kind of the force never exists, right? This is imagination just for the understanding purpose. It's a fictitious force. How it is a fictitious force, we are going to understand this part into the detail. Pseudo force, right? We are going to understand that part right into the detail. Okay. Pseudo force states that, right? First of all, why there was a need of the pseudo force and why it's actually there. So I want to tell you all Newton's law are only applicable in inertial frame. How? Let's have an example to understand this stuff, right? We are having one lift. This is ground. One observer is on the ground, right? There is one lift. The lift is moving into the upward direction with the acceleration A. The lift, it is moving into the upward direction with the acceleration A, right? There is a block of mass M inside the lift. I'm going to show you all the live, right, why there was a need of the pseudo force, right? Why there was the need of the pseudo force. For the observer on the ground, mark my words, for the observer on the ground, the tension is acting into the upward direction, mg that is acting into the downward direction. Tension that is acting into the upward direction and mg that is acting into the downward direction. With respect to the observer on the ground, mark my words, for the first case, this is the first case, right? With respect to observer on ground, if I'm talking about, right? Okay, if I'm applying the conditions of the equilibrium forces, that is MAY, right? Okay, so can I say MA into the direction of the net acceleration forces of higher magnitude minus lower. So here the value of the tension, it is going to come upon as MA plus MG. This observer is on the ground, velocity is 0. For that, this observer, it is known as inertial frame. Why? The frame velocity is 0. This is actual truth observer is seeing. But what happens here? Suppose if the same observer is inside the lift, when he was at the ground, object was appearing, it is moving, accelerating up in the upward direction. Object appears to accelerate into the upward direction to the observer on ground. But same object appears at rest to the observer when he is inside the lift. Now observer is inside the lift. It means that when lift is, right, accelerating, the observer is also accelerating. The lift is accelerating, the observer is also accelerating. Lift is accelerating, the observer is also accelerating. Now what happens here? Here if I am applying the equilibrium condition with respect to observer inside lift, okay, this observer is also accelerating into the upward direction. So this is non-inertial frame. If I am seeing things from non-inertial frame, the equation is coming out as T is equal to mg. This is the wrong equation. The correct equation is this. So why this happens? Newton's laws of motion, right, should be applicable into the all frames. Then why this kind of the problem exists? When the observer is into the inertial frame, we are getting the correct equation. But when the observer is into the non-inertial frame or into the accelerating frame, right, things are getting different. This was the issue. This was the problem, as because of this, pseudo force was introduced. Like that way. Like that way. Okay. Yes or no? Right? Yes or no? Okay. To apply the Newton's law of motion into the right accelerating frame, pseudo force is used. Okay. First point, to apply, right, I'm sorry for this, we need a white pen. To apply Newton's law of motion right in accelerating frame, pseudo force is needed. Okay, to apply the Newton's law of motion into the accelerated frame, right, the pseudo force is needed. Okay, how it is applied? Pseudo force, obviously if it is a force, then it is going to be mass into the acceleration, but this formula is written into the different manner. Pseudo force is mass of the object into acceleration of the frame. The acceleration of the frame is applied into the reverse direction of the force, right? Acceleration of frame is applied in reverse direction. To object, in the reverse direction of the object. Right, this is how things are gonna get easy. Right, on this 3 points entire pseudo force depends. Right, and we are having even the one special case into the pseudo force that we are going to see, but don't get worried. Okay, don't get worried, we are going to see that part later on. Okay, this is the special case, but first of all, on the basis of the pseudo force, we are going to see one sum. Right, on the basis of the pseudo force, right, we are going to see 2 to 3 sums on it, right? Okay, and after that we are going to start the entire part of the friction. After that we are going to start the entire part, right, of the friction. Okay, this question was asked in NEET. This is a wedge, surface is smooth, here block is there M. The question states that how much acceleration A is applied to the wedge such that, how much acceleration A is applied to the wedge such that small m does not slides on wedge. Small m does not slides on wedge. Right, how much for acceleration is here? See, suppose if wedge is getting accelerated, let's say the observer is on wedge. If the observer is on wedge with the accelerated wedge, see, if it is from the ground, things are not gonna work. Wedge is getting accelerated, and if wedge is gonna get fixed, observer is also gonna get fixed. It means it is an inertial frame, but here wedge is getting accelerated. observer is also going to get accelerated. It means pseudo force is needed.
This is the acceleration of the frame. Let's draw the FBD first, right? This is the FBD of the block. This is the normal direction, right? This is mg cos of theta. This is mg sine of theta, right? And this is theta. What happens here? Acceleration of the frame is applied in reverse direction to the block. This is the pseudo force. Mass of the object is m, acceleration of the frame. Now this is gonna have the two components. This is ma cos of theta and this is gonna be ma sine of theta. What does this question states? We want to keep acceleration A is applied in such a way that system should be in stationary. System should be in stationary. So what happens here, right? I'm going to tell you all, summation of all y forces is 0. And I have told many times, whenever you are dealing with an inclined plane and the tension also I have told, right? Always consider this as an x-axis and perpendicular to it as a y-axis. It means that mg sine of theta, that is equal to ma cos of theta. M is gonna, A is equal to g tan of theta. If you are applying this, A is equal to, right, g tan theta of force, if you are applying, right, to the wedge, to the frame, this M is not going to slide down the inclined plane. Right? This is one of the special cases of the pseudo force, right, in which two formulas are there directly, right, without wasting the time. We are directly going to move on through the sums, right. A bob of mass 50 gram is suspended from the ceiling, from the string. See now, trolley, bob is connected initially vertically from the string to the ceiling. Now suddenly trolley starts accelerating. Suppose if the observer is inside the trolley, it starts accelerating. It means that the man is also starting accelerating, right? When frame is getting accelerated, pseudo force, right, is acting into the backward direction. So what happens? Trolley is getting continuously accelerated, right? The bob, right, the pendulum gets tilt at some specific angle and it vibrates. Like this way, it gets tilts at some specific angle and it vibrates. So find the acceleration of the trolley. Simple. Directly we are going to draw the FBD. This is tension. If this is theta, then I must say this is t cos of theta and this is t sine of theta. This is mg. This is acceleration of frame applied in reverse direction to the block. This is a pseudo force. Mass of block, acceleration of the frame. According to the equilibrium conditions, right, summation of all x forces is 0, right? So it means t sine of theta, that is equal to ma, and t cos of theta, that is equal to mg. From this also A is equal to g tan theta is going to come. Theta is 37, A is equal to 10. Tan 37, that is equivalent to 3 by 4. So 2 2s are 2 5s are. Acceleration you are going to get it as 7.5 meter per second square. From this special case of the pseudo force, first this kind of the sums are asked into an examination, and second, from this tension we need to calculate. How we are going to calculate the tension? Squaring and adding this to equation. Equation 1, equation 2. So we are squaring and adding this to equation. T square, that is equal to m under root of a square plus g square. Right? Sorry. T is equal to m under root of a square plus g square. Right? This is 15 by 2. M is how much? 50 gram. Right? So it is, let's take it m, acceleration is 15 by 2 plus 100. It is 15 by 2, so 15 square by 2 square. I'm sorry, 75, okay, 225. So it's 225 plus 400 by 4, right?
So tension is gonna be 50 into 10 to the power minus 3 into 25 by 2. 225 right? Tension is gonna be 625, 0.625 Newton, right? 0.625 Newton. So one, acceleration is calculated, secondly, tension is calculated. Now let's move on to the next sum, right? See. Two small smooth blocks of mass m and m dash are connected by the light inextensible strings and are moving on the smooth wedge of m. If force X blocks that does not slide relative to wedge, find the acceleration of the wedge and the value of the F. Right, applying the pseudo force. Guys, I'm going to give you all this into the homework. You can try, right, an answer of this homework question you can answer beneath the video. Okay, so this was all about the, right, pseudo force. So till now we have seen the important concepts, right, of this chapter. We have seen many type of the forces, right, like a normal reaction and tensions and everything. Okay, now let's move on to the most important part, that is a frictional force. Friction. First of all, I want to write down some of the noteworthy points related to the frictional force, right? The first most important point is it always, right, opposes the relative motion between two contact surfaces. Second point, it is an electromagnetic force. Why it is known as the electromagnetic force, right, we are going to show, right. In another sense, it is interlocking between two surfaces. Right, some of the noteworthy points related to the friction. Okay, now let's understand all of these points, right, with the help of an example. Right, okay, you can see the visualization. Mobile is sliding down and after some amount of the time it stops sliding. Why? Between two contact surfaces we are having, right, something that forces us to stop, right, that opposes the motion, the relative motion. How? Suppose let us take a very simple example. This is a ground and this is an object M. I'm talking about the contact. There exists a, right, there exists interlocking. This is an interlocking between two contact surfaces, right? Interlocking between two contact surfaces like this way. This is the first, this is mass M, the bottom surface of mass M, and this is a horizontal surface. So that is all, there exists always an interlocking between the two contact surfaces, right? Okay, that don't allow the relative motion between them. That is a frictional. Right. Frictional force is not kind of an opposing force, or, right, the students are having this kind of the conception, right? Object is moving like this way, the force that is opposing the motion is friction. No, force that opposes the relative motion. Force that opposes the relative motion, that is a frictional force. So first, it is an interlocking. This interlocking is as because of presence of charges. First, we saw there exists interlocking between the two contact surfaces. This interlocking is as because of the charges present nearer to the charges in contact. They exert, right, towards each other, right, one electromagnetic force that charges, right, exerts right, the charges that are present on the two surfaces, they exert the electromagnetic force, right, with respect to each other. Okay. As because of this, interlocking is obtained, and as because of interlocking, we are able to define the frictional force. Right. So it is an electromagnetic force, right, interlocking between the two contact surfaces. Now, suppose high value of the force is applied, right? What will be the direction of the frictional force? First we define why. What is the reason behind? So the reason is it is an electromagnetic attraction between. The logic, interlocking. What will be its direction? Step to step. Suppose this is an object, high value of the force is applied, this is interlocking. If high value of the force is applied, in anyhow this interlocking will get braked. This interlocking will get braked, right, like this way. Okay, first it was like this, and now interlocking will get break and it will object will move like this way. Right. So in that case, right, what will happen? What will be the direction of friction? The direction of the friction, right, is decided in a way that we need to oppose the relative motion between two surfaces. Direction, again I'm repeating kindly, right, I'm highlighting that stuff, right. The direction of the friction is decided in such a way, right. The direction of the friction is decided in such a way, right, that we can stop, we can oppose, not stop, we can oppose, right, the relative motion between the two surfaces. Suppose this is M, it is moving like this way, na? Friction will oppose it, right? Friction will oppose the relative motion. Suppose it is moving like this way, na? Right? The friction will try to, right, this, right, what we can say, this the upper one, right? It will act into the backward direction for the upper one. Suppose this is M, right? Okay, and this is a surface. Okay, now suppose if you want to stop the relative motion between these two, right? Suppose you want to stop the relative motion between these two, then what we need to do, right? Okay, see, this is a friction is there, right? So friction will pull F into the backward direction and it will push surface into the forward direction. Then and then only the, right, okay, the relative motion between two object, the two contact surface will be opposed, right? Suppose if the particle is moving like this way, right, the friction will try to pull this upper particle, the upper object, into the backward direction and lower into the front direction. This is how the friction is opposing. So in all of these cases, if the direction of the friction is asked, then you always have to consider that it is to oppose the relative motion between the two contact surfaces. Now, let's move on to the formula and the graph. Right. Suppose this is a particle M, right? Okay. Frictional force is always equivalent to mu of N, right? Mu of N. This is a formula of friction, but there exist, right, many kinds of, right, lots of confusions are there in the mind of the students. So for that we are plotting up the graph of, right, frictional force versus applied force. Frictional force versus applied force. Suppose, first step, we are going to classify what is static friction, what is limiting friction, and what is kinetic friction. Static friction, limiting friction, kinetic friction. So let us take an example. If I'm giving the value as 2 kg, right? Okay, and we are taking, suppose, see, M, let us take an example. If we are taking M as 2 kg, right? If we are taking, right, M as 2 kg, right, and mu as 0.2, right, this two data, suppose I am taking, what will be the maximum value of the force needed so that this particle can, right, so what will be the maximum value of the force needed so that that can be the relative motion between the two contact surfaces. That should be the relative motion between the two contact surfaces, right? So for that, first of all, I'm going to calculate the limiting friction, right? FL, that is equal to mu of n, right? So that is 0.2 normal. This n is in upward direction, this is in mg in downward direction, right? So 0.2 into 2g, that is equal to 4 Newton. The value of the limiting friction is 4 Newton that we calculated using the formula, the simple formula of friction. We calculated it, right? Now what is this value 4 Newton is? The name itself states limiting friction. The name itself states as limiting friction. Now what actual the limiting friction is? Right? The name itself states as limiting friction. The maximum value of the friction up to which interlocking will not get braked. The object will not start the motion. The maximum value of the friction, that is limiting. The name itself states in a limiting friction threshold value up to which the particle will not start. After this, interlocking will get braked and that object will start moving. What will happen beyond the limiting, before the threshold value and after the threshold value? Suppose we got this thing. Suppose if 4 Newton is applied to this specific object now, right? Okay, then it will be on verge of moving. What will happen? The value less than 4 Newton, and what will happen, right, to the value greater than? Suppose, first case, F is 1 Newton applied. Interlocking is a crazy phenomena. Limiting friction is 4 Newton. Before limiting friction, there exists static friction. Why it is named as static friction? Because in that entire phenomena is going on, object is not moving. That's why it is named as static. See, to move this object, 4 Newton is applied. 4 Newton is needed. To move this object, 4 Newton is needed. How much amount of the force we have applied? 1 Newton. 1 Newton is less than 4 Newton? Yes. Object is going to move? No. Why? Static friction is self-adjusting friction. Static friction is self-adjusting friction. According to the external force applied, static friction adjusts its value. Suppose if 1 Newton is applied, friction will adjust its value and will make 1 Newton. Suppose 0 Newton is there, friction is 0 Newton. Suppose 1 Newton is there, still object is not moving. Static friction will self-adjust itself and increase its value to 1 Newton. Right? Okay, the graph will be like this way. Now this F is getting confused. Why object is not moving? So he thinks that let's increase the value of F. Suppose if I'm increasing the F to 2 Newton, again static friction will self-adjust and it will try to save this interlocking. So if external force is applied is 2 Newton, right, static friction will self-adjust to it. The graph will be straight line. Up to what limit the static friction will try to self-adjust? Now the external force applied is 4 Newton, right? Again the static friction will be 4 Newton, right? Okay, so suppose this is a 4 Newton, right, and this will be the 4 Newton, right? So this will try to self-adjust up to this, right, like this way. Now we have reached to the maximum value of the static friction. The maximum value of static friction is limiting. When applied force was 0, static was 0. When applied force was increased to 1, static self-adjusted and increased its value to 1. When applied force increases to 4, static friction try to self-adjust its values and increased it to 4. But now it has reached to the maximum value of the limiting. This reached to the maximum. Now if applied force is increasing its value, static friction is not going to do anything, right? It will be, nothing will be in its hands, right? Because the external force values has reached to the value of the limiting friction. It means that, right? It means that, right? The object is on verge of moving. So at this point, object will be on verge of moving. So from this to the maximum value of the limiting friction, object is stationary, and that's why we are using mu s, that is known as coefficient of static friction. Now after this, suppose if I'm applying F as 10 Newton, whoa, interlocking will break. Why? Our limiting friction value is 4 Newton. But we have applied more than 4, that is 10. Interlocking will break. This section of the graph, right, shows the interlocking has gone. Why? Because we have applied the value of 10 Newton. And that external force, that value we have applied, it is the value of external force and it is greater than limiting friction. After this, suppose if I am applying, right, after this, now object is in moving. So whenever the object is moving, we are having the kinetic friction. So it means here the formula will be mu k of n. Always mu k value is less than mu s. Why? Because here in mu s interlocking is not getting break, but in mu k interlocking is getting break. That's why the graph is like this way. And after that, value of the friction will be constant till end, and that value will be kinetic friction. Right now, after that, if you are applying suppose 1000 Newton also, then like suppose if you are applying 1000 Newton. Once it has crossed the limiting value, right, kinetic will be constant till infinite, right? Kinetic will be constant. Right? So what the entire process tell? First, we need to calculate the limiting. Suppose limiting is 4. Now, external force applied is 0, static friction self-adjusted. Applied force is 1, static friction self-adjusted to 1 and save the interlocking. External force applied is 4. Now static friction has reached to the maximum value, that is its limiting value. Right now the object is on verge of moving. Now after that, suppose if Fx external force is increasing its value, then that static friction is not going to do anything. So after that, right, suppose if 10 Newton is applied and it has crossed the limiting value, interlocking will break. Now the static roll is ends here. Interlocking will get break. Okay, one jerk is obtained. This is jerk. That shows the breaking of the interlocking, jerk. Right, and after that, here comes the role of the kinetic friction when the object is moving on rough surface. Right, and after that, suppose if external applies, right, 1000 Newton, then also the kinetic friction is constant. So the graph is like this way. Right, graph is like this way. It starts from here, right, it moves to here, and it's like this way. Right, so this is what an actual concept, and value of the kinetic friction is always less than coefficient of static friction. Mu is the coefficient of the kinetic and static friction. that you all are aware of. In some of the cases, right, this jerk is so negligible that mu s and mu k is considered as equal. In some cases, jerk is negligible, then this both are considered as equal, else kinetic value never exceeds, right, okay, to the limit, this static value. Okay, so this was an actual graph. Okay, now after that, okay, first of all, let's see sums, right, related to this, and then we are going to solve, right, the sums of the right, two block systems we are going to solve. Okay, now see, a plank with a box on it, there is a plank with a box on it, it is gradually raised about the other end as angle of the inclination with the horizontal reaches 30 degree. The box starts to slip and it slides down 4 meters in 4 seconds. The coefficient and stri are will be, okay, coefficient of static and kinetic friction will be respectively, right? So in this case we need to calculate the both, right? In this case we need to calculate the both. It's a very simple thing, right? Suppose mg, okay, mass, okay, mass is given. Okay, the box start to slips and slide 4 meters down the plank in 4 seconds. The coefficient of the static and kinetic friction. Okay, first of all, let's draw the FBD.
Suppose this is mg, this is the value of n, right? This is mg, right, cos of theta, right? Okay, this is mg, right, sine of theta. This will be the value of the friction, that is equivalent to mu of n, right? Okay, this value will be equivalent to, right, mu of n, friction, that will be equivalent to mu of n, and this will be the direction of net acceleration.
This question is asked into 2015 question in 2015, and it's really nice, right? So see, we draw down the right, okay, now what will be the value of the net acceleration? Mass is not given, right? So can I write it down? Net acceleration into the downward direction, that is ma of net acceleration. Net acceleration is in downward direction, right? Okay, so as I said before, whenever we are dealing with an inclined plane, always consider the inclined plane surface as a x-axis and perpendicular to it as a y-axis, right? So it is in the downward direction, right? Okay, so this will be the higher and the friction will be the lower magnitude. So it's mg sine of theta minus mu of n, right? It's mu k of n, because object is moving, that's why we have kept it as a kinetic friction, right? Object is moving, that's why we have kept it as a kinetic friction. So m will get cancelled, so a net, that will be equivalent to g of sine theta minus mu g, this will be mu k g cos of theta, right? Can I consider this as equation number 1? Yes. Now, as I said before, when the object is stationary on the surface, there exists an interlocking, right? So at that position of the time, we are having the coefficient of static friction, right? But in this case, we will be having the right coefficient of the kinetic friction. Okay. So whatever the values we are getting from the coefficient of kinetic friction, and after that we'll show you the coefficient of static. Okay, now see, a net is equal to g sine theta minus mu g cos of theta. Okay, now in 4 seconds it is traveling 4 meters. In 4 seconds it is traveling 4 meters. So it means that suppose from position A, u is 0, it is reaching to position B, it is moving down with the net acceleration. 4 meter distance is traveled into the 4 seconds of time interval. Acceleration is constant. Can I write it as sc is equal to u of t plus half at square? From here, the net acceleration we are getting it as 0.5 meter per second square. Right? Can I replace this value here? Right? So it will be 0.5 is equal to g sine of 30 minus mu of k g cos of 30.
right? So it's 5.5 is equal to G by 2 minus mu of K G root 3 by 2. Okay, so it will be 1 is equal to G minus mu K G root 3, making G is common, right? So 1 is equal to G 1 minus mu K root 3, right? So 1.1 is equal to 1 minus mu of K root of 3, right? So mu of K root of 3, that is equal to 0.9. So mu K, that is equal to 0.9 whole divided by root 3, right? 0.9 whole divided by root 3. So this is the value of the coefficient of the kinetic friction, right? Okay, this is the value of the coefficient of the kinetic friction, right? Okay, we are going to obtain it here. Okay, don't get worried. First of all, we are going to we completed the entire procedure, just the final evaluation is remaining. Now, what about coefficient of the static friction? When object is stationary, then and then when interlocking is there, right? So it means that when the object was about to slide for very small amount of the time, there exists the there was a presence of static friction. It means that when we need to keep the object as rest, then and then we can calculate the concept of the then and then we can calculate the value of the coefficient of static friction, right? So at this point of time, if net acceleration is getting 0, friction and mg sine theta will get balanced, will get the value of the coefficient. Because the object is stationary, what will be the value of the friction? Mu of n, that is equal to mg sine of 30, right? Mu of n, that is equivalent to mu of n, that is equivalent to mg sine of theta 30, right? What I have to write here? It should be mu s or mu k. It should be mu s. Why? Net acceleration is 0, object is stationary, and whenever the object is stationary, we are having static friction, right? So here mu s mg cos of theta, that is mg sine of theta. mg is going to cancel. Mu s, that is equivalent to tan of theta. So mu s, that is equal to 1 by root 3. This is the value of the coefficient of the static friction, right? This is the value of the coefficient of the static friction, right? And this is the value of the coefficient of the kinetic friction. Now we need to evaluate this, right? We need to evaluate this part. So the value for this static friction, it is equivalent to 0.6, okay, and this one will be approximately equivalent to 0.5, okay. So I think that D is the perfect answer for this specific question, right? Okay, now let's move on to the next. See, a system consists of 3 masses M1, M2 and M3 connected by a string passing over a pulley P. The mass M1 hangs freely and M2 and M3 are on the rough horizontal surface. The situation is like that, right? This is a rough horizontal surface with a coefficient of the friction mu, right? Okay, this is a pulley connected. I'm sorry, right? This is a pulley connected, right? Here M2 is connected, and with M2, right, M3 is connected, and M1 is hanging freely. Situation is like this way. What we need to calculate? We need to calculate the downward acceleration of the masses, right? Downward acceleration of the masses. It's very simple stuff. Okay, can I say that the formula for the net acceleration? See, suppose if it is moving into the downward direction, then it will be the net acceleration. Then these 2 blocks will move into the left direction. Suppose if M2 and M3 are moving towards the left direction, right, the relative motion is like this way, so friction will try to stop it, so it will act into the opposite direction, right? So this will be mu M2g and this will be mu M3g. What will be the formula of net acceleration? That will be net force whole divided by masses of system, right? All of those tensions are getting cancelled. Suppose here we are having T, Okay, then here we are having T. Suppose here we are having T1, here we are having T1, right? So what will be the net acceleration? T minus T plus T1 minus T1, right? Plus, right, weight that is acting into the downward direction, that is m1g, minus, these are the opposing forces, okay, m2g minus mu m3g, whole divided by mass of system m1, m2, m3. Now all of those masses are equal as mentioned, right? m1 is equivalent to m2 is equivalent to m3, right? Okay, now so the net acceleration of the system in this case will be, see, all of those tensions will get cancelled, right? So it is okay, m will also get cancelled, right? So I think finally we are having it as a, right, 1 minus 2 mu g whole divided by 3. This is a net acceleration of the system with which m1 is moving into the downward direction. Okay, so the C will be the perfect answer for this specific question. C will be the perfect answer. Okay, now let's move on to the next part. A block B is pushed momentarily along the horizontal surface with an initial velocity v. If m is the coefficient of sliding friction between B and the surface, then block B will come to the rest after what time? Initially it is moving with the velocity v. After some time the velocity of the block is getting completely zero. The velocity of the block is getting completely zero. It means some, right, a retardation is present that is opposing the motion of an object and decreasing its velocity. You can see the velocity is in this direction, acceleration is in opposite direction. It means acceleration is opposing the motion of an object. In another sense, it is retardation, right? So here it's very simple. This retardation is provided by the rough surface. So guys, just keep one thing into your mind. Whenever the retardation is provided by the rough surface, it means by friction, then that value is always equivalent to negative of mu g, right? That value is always equivalent to negative of mu g. You all are aware of this stuff, right? So this is constant, right? So let's apply the equation of the motion in this case, right? Let's apply the equation of motion in this case. So we will have v is equal to u, right, minus mu g t. Final velocity will be 0, u minus mu g of t, right? This is v. So time to stop will be v by mu g. And this will be the perfect answer for this specific question, D. Right? Okay. Okay. Apart from this, right, this question I've given you all into the homework, but we can solve it. Let's solve this stuff. The coefficient of the static friction mu s between block A. Okay. This is mass 2 kg. Coefficient of the right static friction is value is 0.2. Right. System is like this way. Okay. Now, what would be the maximum value of the mass of block B? So that what will be the maximum value of the mass of B so that both blocks should not move, right? Do not move. See, if it is written, it is mentioned into the question that both blocks do not move, it means that net acceleration of the system is 0. The downward acceleration of the A is 0. Right, the right side acceleration A is 0. It means all of the forces are balanced, right? All of the forces, they are balanced, right? So here tension is in upward direction, right? Weight of B is in downward direction. Tension will be in this direction and it is balanced by the frictional force. So here tension is balancing the weight of MB. Same string is connected to A. So that same tension is balancing the friction. So in another sense, if tension is balancing the friction, right? If tension is balancing the MBG, in another sense, friction should balance MB, the weight of the B, right? Now, what is the friction? Mu, right, into 2G, that is equal to MB into G. G will get cancelled. Value of the mu is 0.2. into, that is equivalent to mass of B. So mass of B, that is equal to 0.4 of, right, kg. If this much amount of the mass is given to the B, the system will not move. See, actually the acceleration 0, it means there are two ways. Net acceleration 0, it doesn't mean system will not move. There is a possibility, right, that it can move with a constant velocity because forces are balanced, right? Net acceleration is having the two sense. Okay, net acceleration is equivalent to 0. It is having the two senses, right? One, velocity is 0, right? Second, velocity is constant. So if you are putting 0.4 kg, then there is a possibility that system can move with the constant velocity. But more than that, system will get stopped. Okay, so the D will be the perfect answer for this specific question. Right. So guys, this is a homework, right, question from my side. You can answer this homework question beneath the video, right? Okay, even this is also the homework. Very nice sum to calculate the friction, right? Okay, this is also from my side. Okay, and let's move on to the two block system now. We are going to see only two sums of the two block system, but really we are going to, right, grab that thing into the mind. Two block systems, right? The next 10 minutes to do this systems, right? And we are going to stab it. Okay, see, suppose this is a surface, right, where coefficient of the friction is completely 0. This is a 3 kg mass, right? This is a 4 kg mass. Here coefficient of friction is 0.3. What will happen? What will happen? Suppose if F is applied to the lower block, what will happen? If F is applied to the lower block and value is quite high, the lower block will move into the forward direction and the upper one will move towards in the backward direction. The lower block will move into the forward direction and upward will move into the backward direction. Is it true? Yes, obviously it is true. But here we haven't defined the value of F. At what value of F this will happen? At what value of F this will happen? That's an important step, right? Lots of questions we are having. At what value of the F the system will start moving? At what value of the F they both will move together, right? Because the possibility is that the force is applied to the lowermost object. So there is a, what we can say, there is a possibility it may move into the forward direction and 3 kg can move, it can be pushed backward. We don't want to do that. We want that value of F, right, up to which these two blocks can move together like this way with a common acceleration, right? So let's draw the FBD for it. Okay, this is the 3 kg, right, and this is a force applied. As I said right into the beginning of this, the concept of the frictional force, as I said, it's very, very simple. Friction means to oppose the relative motion of the two contact surfaces. At the bottom level, friction is not there, means the system is going to slide, that is fixed. So whatever it will go on in between 3 kg to 4 kg, right? Possibility of a relative motion that can occur in between these two blocks is like this way. 4 will move into the forward direction, 3 will move into the backward direction, right? So in this case, friction will try to oppose this relative motion. So for that, friction will force, right, 4 kg, it will pull 4 kg into the backward direction and it will push, right, 3 kg into the forward direction. The force is like this way. Friction for 4 kg block will act like this way, right? Okay, this direction of friction can only oppose the relative motion between the two contact surfaces. This is what friction is all about, to stop the relative motion between the two contact surfaces. Both are having the common acceleration A, because we want that value of F, right? Okay, up to which they both will move together. First of all, let's use this 3a, that is equal to friction. So 3a, that is equal to mu. Now what is the normal? And here it is in upward direction, and this will be equivalent to 3g, right? And the bottommost, right, and 2, it is 3g plus 4g. At the bottommost surface, we are having the weight of the whole system. So that's why at the bottommost part, we are having the reaction as 3g plus 4g. And in between these two blocks, we are having the reaction of 3g, because only the load, the weight of the 3 kg is applied on it, on this contact surface, right? How much load you are applying on the contact surface, the amount of the reaction it will produce. Similarly, 3 kg is applying 3g amount of the weight on that contact surface. So we are having the reaction of 3g. Similarly, at the bottommost part, the entire system is, right, applying the load. So we are having the, right, 7g as a normal. Here it will be mu into 3g, right? So acceleration will be 3 meter per second square. This can be the common acceleration of the system, right? Now, what will be the value of the force, right? So can I say 4a, that is equal to F minus 9. So F will be 12 plus 9. F will be, that will be equivalent to 21 Newton, right? F will be equivalent to what we got. We got the maximum value of the F. See, I'm writing the 3 criteria here. First, if F is less than 21 Newton. Suppose, see, external force completely depends on us. In this kind of the sums, first of all, we need to check, right, the threshold value. Then how much amount of, at what value of F both will get separated. This we need to check, because by doing so, right, okay, it is really going to help the sums to solve the sums easily. If F is less than 21, right, F is less than 21, okay, both will move together with the common acceleration. Right, if F, that is equivalent to 21 Newton, the both blocks are on verge to get separated. And third, if F is greater than 21, they will be separated with the different accelerations A1, right, and A2. They both will get separated with the different accelerations A1 and. So less than 20, this is 21 is our threshold value. Less than that, they both will move together with the constant acceleration. That is, it's not a big deal, right? Okay. More than that, they will get separated. At 21, they are about to get separated like this way. The moment before separation start, just a moment before the separation start, that is the moment of F is equal to 21 Newton. Now suppose same example we are taking, 3 kg, 4 kg, mu is equal to 0.3. Now this time I'm taking the friction at the bottommost part also as 0.2. Now how much amount of the F is needed? How much amount of the F that is needed, right? How much amount of the F it is needed? Simple. Half of this sum we have already done. Okay, let's draw the FBD. Okay, this is a 3 kg, right? This is a 4 kg. F is acting into this direction. Similarly, the friction 1, right? Both are having the common acceleration, right? Now there is another friction. In previous question, if I'm talking about, right, the coefficient of the friction at the bottom of the bottommost part, right, bottommost surface was completely, right, it was not rough, it was smooth. The system was easily sliding on that. The lowermost block was easily sliding on that. But in this case, we are having the friction. It means that
for entire system, we are having the another value of the friction, that is FR2. In previous case, F was applied in such a way that they both shouldn't get separated. We got the maximum value of the F. In this case, first F need to think about to overcome this value of the FR2, then system will move, and on the third step blocks will get separated. In previous question, on very first step, if you are applying less than 21 Newton, they both will move together, right? If you are applying greater than 21 Newton, they both will get separated. Only two priorities were there. Here we are having three priorities. First of all, we need to overcome the friction of a ground on which the entire system is placed. Then we have to move on to the next step. What will be the value of F? They both, for that value, they both should move together, right? So in this case, see, again 3A, that is equal to value of friction 1. A is again 3 meter per second square. We are getting the common acceleration as 3 meter per second square. Now this time 4A, that will be equivalent to F minus friction of 1, right, plus friction of 2. So F will be 12 plus friction of 1 plus friction of 2. Friction of 1 you all are completely aware of, right? N1 in this direction, the load applied, that is equal to 3G, right? So the friction of 1 will be 12 plus mu. Mu is 0.2 into 3G. Plus, what about this friction at the bottommost surface? See, I'm talking about the contact surface between the 3 kg and 4 kg of the particle. So in between that, right, okay, only 3 kg load is applied. So for that we are having the reaction of 3G. But if I'm talking about the bottommost surface, 3G plus 4G, 7G of the load is applied, and for this, at this bottommost, right, we are having the normal, right, of 7G. And what is the friction value point? Here we are having 0.3, and this will be 0.2 into 7G. So here it will be 12 plus 9 plus 14, right? So this will be 35 Newton. In the previous question, we got the value of F as 21 Newton. Why that was less? Because at the bottommost part, friction was not present. But in this case, we got the value as 35 Newton. Now let's understand this final stuff first. If 0 is less than F, what is the value of the FR2? That is 14 Newton. If F applied is between 0 to 14, right? If it is between 0 to 14, right? Then what will happen? It's a very simple thing. Okay, system will not move. Entire system will not move. If system is not moving, right, how we are going to identify whether the blocks will get separated or not? If system is not moving, then how we are going to identify whether the blocks will get separated or not? So F is greater than 14, system will move. Second, in between 14 to 35, right, both blocks will move together with the common acceleration, right? F greater than 35, equivalent to 35, they will be on verge of moving, right? They will be separated with a different acceleration, A1 and A2. So students, again the lecture of the Newton's law of motion ends here, right? Okay, the lecture of the Newton's law of motion ends here. Okay, so I think it's time to go, right? I will be waiting for all of the feedbacks beneath the video regarding this lecture, right guys? So this is Indrajit Singh. Again, we are going to come back into the next lecture of work, energy and power. This is Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bachaji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye Bachaji.